games.
Inhomogeneous, spatially inhomogeneous.
Spatially
Evolutionary game.
Yeah. Okay, so let's start this morning session with Massimo Fornasier from Munich, and he will talk about it's very inhomogeneous. Spatially inhomogeneous evolutionary games.
Thank you. So, first of all, I would like to thank all the organizers for inviting me here. It was a very intensive moment. And I would like to introduce you to a new type of evolutions that we considered with some co-authors, with Luigi Ambrosio, Marco Morandotti, and Giuseppe Savaré. For that, I would need to mention a little bit something about evolutionary game. My understanding of this topic is a bit in analogy with what comes into physics. So, in physical systems, the physical system tend naturally to converge to a steady state, if you want, by following the Newton law. And once it's there, it stays there until the conditions change. And so, since frequently physical systems are supposed to visit these steady states, well, it's interesting to study them. So why study the evolution? We can simply study the minimizers of certain energies and looking at what happens if the conditions are changing. So we get maybe into other type of evolution, like quasi-static evolution, where you are hopping from one steady state to the next, and so on. Similarly, game theorists, they have been very much interested to the concept of game equilibria, assuming that sooner or later, whenever you have a dynamical situation where driven by a game, sooner or later you end up in a such equilibrium, and so it's interesting to look at equilibria. Probably the most famous concepts of equilibria is due to John Nash. That has been building on the concept of mixed strategies, and we will see what does it mean for us, mixed strategies, in this talk. And however, somehow even earlier, Morgenstern and von Neumann, they were kind of interested to the idea of having a dynamical approach to games, rather this static concept of solution where you simply look at equilibria. So the idea is that in physical system we have a Newton law. What about for games? Is there anything that could be seen as a sort of gradient flow, natural gradient flow for games that converge to certain equilibria? So let's see what could be a good notion or some notion of dynamical game. One of the most advocated mechanisms in the field seems to be, to our literature search, based on a selection principle inspired by a sort of Darwinian evolution concepts. So in particular, somehow you would like to reinterpret the probability of picking a certain strategy as instead the distribution of the populations of players adopting these strategies. So the idea is that you have somehow a space of strategies that you can pick, and you have a probability distribution over this set of strategies, and these represent the amount of population that is choosing a certain strategy U. Okay? So you are, instead of considering it as the probability of choosing a certain strategy in your game, for us in this first part of the talk, it's more a population distributed over the strategy space. So the emergence of certain steady states in a dynamical game is a result of evolutionary selection. So one player or some player that is usually playing strategy U somehow plays against the other players and sees how good is his strategy with respect to a certain payoff. And if this payoff is quite advantageous, then you would like to subtract a little bit of mass from the other strategies and increase that strategy. Okay, and the steady states are essentially representing eventually a sort of tendency of promoting the best strategies that a population may want to choose. Okay, so that's a bit the idea. We will make it a bit more rigorous from a mathematical point of view. Will be clearer, and so on. So the payoff determines the frequency that a strategy should have, and somehow we try to increase in that direction So to start, we consider a finite number of strategies picked into a suitable compact set of strategies, and we denote with sigma I the corresponding frequency with which players pick strategy UI. And we do have a payoff functional that somehow tells you whether strategy UI with respect to strategy UJ is better or not. So the higher is the payoff, the better. And to understand whether a certain strategy is doing well, you consider this strategy against the entire population that plays the other strategies. Okay? And you subtract the overall payoff of the game. So in a certain sense, everybody is playing against everybody. Okay, this is the total payoff. And if I play strategy UI and my payoff is larger, then in a certain sense, this delta is promoting that type of strategy. The way of promotion comes, of course, by increasing the relative rate of change. Increasing the probability distribution in that point, hence the relative rate of change is really proportional to this quantity. Okay, it's like taking a bit of mass and put it in the strategies that you want to promote. Okay, and you go on with this kind of iteration, and somehow this is called a replicator equation in the field of evolutionary game theory. Why this is interesting? Because somehow omega limits or sets of accumulation points of these dynamics or the steady states are actually closely related to Nash equilibria. More formally, somehow if you have a Nash equilibrium of the game related to this particular table, which is a payoff matrix, then it is a rest point of this kind of evolution. If it is a strict Nash equilibrium, then it is even asymptotically stable. So if you start very close, then we will end up there. A rest point is that is a limit of an interior orbit in the simplex. Then it's also a rest equilibrium, a Nash equilibrium, and a rest point is stable. Then it is also a Nash equilibrium. So they are very closely related. Although they somehow in general, the replicator equation is not known to produce always somehow a Nash equilibrium. Sometimes you converge to some other type of equilibria, or you might also converge to a kind of periodic orbits or visiting strange sets. So it's not necessarily somehow the method to converge to steady states that are Nash equilibria, and it would be interesting to understand where it does converge and what is a general way to understand that. In order to do that, maybe it would be interesting to consider the mean field approximation. So whenever you consider a very large number of particles, so instead of having only n strategies, you want to consider now a sort of continuum set of strategies, and now we are really addressing a probability distribution over the compact set U. And you can rewrite somehow, whenever you write this in this form, you can rewrite the interaction potential as really in terms of somehow integration with respect to the probability distributions, and eventually by taking the limit for n going to infinity under proper compactness assumption, you can rewrite the equation in a weak form, and you end up with this kind of equation. Okay, so it's a mean field type of equation. So. Well, we mentioned at the beginning gradient flow in physics. What about here? Is the replicator equation any sort of gradient flow? So, talking on this issue with Giuseppe from the very beginning, when I saw this equation, said, well, it's very likely just a Hellinger flow. So. Well, the Hellinger distance has been already mentioned in the talk of Mielke, and somehow it's related to a reaction type of equation, and with a quadratic cost, and this is essentially a distance between positive measures. However, it has also a very interesting explicit expression in the terms of the densities of these positive measures with respect to a reference positive measure, and it turns out that actually this expression is independent of the particular measure on which you are taking this Radon-Nikodym derivatives, and if you want to rewrite this in terms of distance between probability measures, you end up with a so-called spherical Hellinger-Kakutani distance that can be expressed in a certain sense either requiring that evolution is in the probability space, or correcting the dynamics by subtracting somehow the mass, so that you have a sort of here conservation of the mass from the very beginning, right? So either of the two would function for defining the distance. And if you look at the expression of this particular term, you see that on the right-hand side you have exactly this subtraction of mass that is intervening in the dynamics. Interestingly enough, you can express the spherical Hellinger distance in an explicit way, and you end up that is really expressed in terms of the Hellinger distance. And so that you have an explicit expression with respect to the densities and so on. With this, you can play, and somehow, if you consider a general functional and you consider a corresponding minimizing movement scheme, where you move now with respect to this spherical Hellinger distance, and you consider formally the limit of this discrete time steps, you end up precisely in an equation of this type. That is for the case where the functional is minus somehow a functional of this type. Somehow it's indeed a gradient flow to minimizing this functional, which means that it's a gradient flow in the sense of ascending gradient flow to maximization of this payoff functional in terms of the Hellinger distance. Okay, so we see that there is already some transport going on at the level of this kind of game, but it's actually not what we are interested in. The idea is now to change paradigm significantly and modifying the scheme, and going back to reinterpret any probability distribution that you have here on the strategy space, not anymore as a probability of picking a probability that describe a population distributed over this set, but rather the probability of picking a certain strategy. Okay? So now we would like to create a dichotomy. We split the population from the strategies to choose. And we would like to endow every element of the population with its own mixed strategy. So now I'm following, in a certain sense, an approach in the sense of the talk Benedetto Piccoli, and we introduce a sort of evolution of measures in the sense of what Benedetto presented at the very beginning, which is, in our case, the wrong modeling. And I'll try to explain why it is wrong and what induced us to move to a further level of abstraction. So now, what we would like is a spatially inhomogeneous replicator dynamics. So we saw before that we have no space intervening. We have just a sort of dynamics going on at the level of the population distributed over the strategies. Now we want to split the space into a space where somehow the players have a certain position, and each player will be endowed with a strategy that is using to pick at random the next move to move in the space Rd. Each player probability distribution at the same time is supposed to evolve according to a replicator dynamics that now takes into account all other players and the respective mixed strategies. So this is a bit the idea. So now every player, it's like when you are in the freeway or in the autostrada, and somehow all of a sudden your lane gets stuck, but the others is free. At this point, you are flipping the coin and deciding whether you stay in the lane where you are or rather move to the next lane and you move forward. Okay? So that's a bit the idea. And of course, when you move there, the probability of what you're going to do has to change. And so you have to dynamically move according to a certain probability, and at the same time changing your probability of moving according to the new setting. Is everybody with me? Okay. So, very good. So how do we do that? In the wrong way. Well, first of all, we have to augment somehow the space where we are considering the game by the space of the positions. And now the payoff functional is based on the crossed Rd times U times Rd times U. And at every time step, discrete time step, we consider an empirical distribution, so of agents distributed on Rd. It's just to simplify, and for each player supported on this distribution here, n is missing, we assume that we are given a corresponding mixed strategy, so a probability distributions of strategy that we can use. And by using these two probabilities, we form a probability by integration or disintegration of that probability on the cross space, which is exactly what Benedetto was thinking in a certain sense. And then we define formally a deterministic stochastic type of evolution of this particular agent by saying that its mixed strategy needs to move according to a replicator equation, where now the interaction potential is really integrating somehow the payoff functional with respect to each player, each other player, and their corresponding mixed strategies. So we are integrating with respect to eta, and we take away the entire payoff with respect to, in a certain sense, saturating the strategies that I may use. So this is the efficiency of the strategy U played by the player X with respect to all the strategies that he can play against somehow the entire population. Okay? So this is a new kind of replicator equation in this inhomogeneous setting. At the same time, everybody moves, or this player is moving according to a field that is some field E that is function of the strategies. And what we want is that the strategies are drawn at random independently according to this the corresponding probability distribution at the next step. Is everybody with me? It's very important to understand somehow how it works. Any question? Yes?
How do you relate the function e with the step, with the preceding step?
The function e?
Yes. This is the velocity in which sense?
Well, it's an arbitrary vector field. It's an arbitrary, so it's a function that takes one point and one strategy and gives you a velocity.
So it's a pointwise strategy at the step, at the given step, the u there.
The u is a pointwise strategy drawn at each discrete time according to this probability distribution. So this is a stochastic step. You with me? This is a very deterministic, but this is stochastic. Okay? Yes?
So, I mean, you're doing two things at the same time.
Yes, you do two things at the same time.
And you're randomizing the strategies. Why do you do that at the same time? Why don't you first randomize strategies and then, is there a particular reason for
No.
doing that?
No, it's simply that it's very simple to explain that. So you try first to somehow, in this discrete time evolution, you first update the strategies according to where you are supposed to be in the next step somehow, and then you draw it random according to that, or vice versa. You can do both. There is no particular reason, no.
So, but you could also, without introducing space, just kind of randomize the strategy.
Without introducing space,
Yes.
I'm not understanding maybe we can talk later. I didn't understand what you mean without. So we want to have a space where the agents move. So we need the space. And the way they move randomly according to a probability distribution that depends on the agent. Okay? And these also evolve in time. So the next time somehow you want to update this probability distribution to be sure that in the next situation the system is, you change your behavior. And this change of behavior depends on a game that everybody plays against everybody.
So there is no random here. So sigma is the distribution of probability, but there is no other omega behind.
But every player, I mean, even if the X was not there, every player would choose at random something out of this strategy, out of this strategy.
But sometimes he knows the distribution sigma, and he moves according to this distribution with the law given by T.
So as opposed to the previous model, you're introducing randomness. Because at every step you're making a random.
Yes, so I mentioned that now you have to think about sigma not anymore as a distribution, a population over the strategies, but as the probability of picking a strategy. You okay?
That's what I mean by.
Yeah, exactly. We went back to the concept of game a la Nash. Okay. Okay, so what happens to this eta, how that eta t is evolving? So we can consider this kind of finite difference in time. Then we plug what we wrote so far into the sort of testing the equation in the two variables. Then we add and subtract some terms so that here we have a difference in phi, and here we might have a difference of the strategies. The difference of the strategies is ruled by the replicator equation, and so what you get here, if you do a first order approximation with respect to the Taylor expansion of phi, you get that the gradient of phi is supposed to be evaluated against the average strategy picked by the agent xj. And at the same time, here you have to remember what is the difference between these two guys. That is exactly h times the interaction potential. And if you now approximate this term by using the previous term, you can approximate once more up to a h approximation somehow with an integration of overall this term with respect to the eta. So now if you take formally epsilon to 0, what you end up is the following evolution with respect to this somehow joint probability distribution with respect to x and u. And if you now want to see what happens in the distribution of the agents, you simply integrate this with respect to a test function that depends exclusively on the space, and you end up on an equation that is very well defined for the distribution of the agents, and where you have a very nice transport term and another term that is purely reaction term. And that's the reason why this is the wrong model. Because in a certain sense, it tells you that you can teletransport. Okay, this is pure transport, is really movement. That's exactly the modeling that we wanted to have in mind. But here you can move mass from one physical point to another physical point without transport, okay, simply because it's more convenient in the sense of the game. Okay, so it's more convenient in the sense of the game, so you better move there where the game is fun. Okay, you get more a better payoff with respect to where you are, and you jump over there, which is not the model that we wanted to have eventually. Okay, so this very nice idea at the particle level, if you want to include it into this particular evolution of measures, is not modelistically consistent with what we had in mind. Okay, it's plausible, makes sense, but it's not what we wanted. And this is exactly somehow the point of starting of discussion with, for me, with Giuseppe, and then with Luigi, because somehow I had in mind this idea of this inhomogeneous evolutionary game, but I ended up with something that was absurd, and I was kind of confused by that, and that's why we needed to make a further step of abstraction. And the further steps of abstraction require to somehow move the attention from a probability distribution of the cross space between RD and the probability distribution of the strategies to the cross space RD to U to the cross space RD mixed strategies, P of U. Now we see how that works. Okay, so now the state space is not anymore RD times U, but is RD times the probabilities over U. And so we will end up on transport equations in the space as curves in the space of the probabilities over RD times the probabilities over U. And so in a certain sense, a partial differential equation over a non-Euclidean and infinite dimensional space. Now, the elements are really x and sigma, and we will consider distributions over the spaces. So in particular, we will consider a certain sigma and evolution within this space that represent the distribution of players and their strategies. Okay. Now, the corresponding new interaction potential will be taking into account now that the success of a certain strategy U with respect to X in a position X will be integrating with respect to the strategy of the other players, and then considering integration of the distribution of all the players and all the strategies. Okay. And so we have again the same kind of construction. It's just the fact that we had now to further somehow considered a independent somehow probability distribution over the mixed strategies. I know it's kind of further step of abstraction that takes a little bit of effort. Okay, so this is the correct approach. So we first of all would like to construct a probability measure over the paths, so over evolutions and curves into the space. And the way we do it in on a discrete time approach. First of all, each player, somehow it's a player that is in position x bar in a certain time t, is having a certain mixed strategy sigma bar, is evolving its a mixed strategy according to the replicator equation. And then the conditional probability relative to the path in this interval 0t plus h of the next move of this player with strategy sigma t plus h is given the information that it was in a previous position, is given precisely in the terms of randomizing the next step in space as we did before, but knowing that the next probability distribution is this one. Okay, so this is the way you embed the same logic that we saw before into this setting. Now we have a probability distribution over the path driven by these dynamics, and we can consider the evaluation of this at every time t. And so in a certain sense we can restrict our attention to certain time t, obtaining a probability distribution sigma that still depends on our discrete time step h. Okay, let's see what happens evolving this sigma. We do exactly as we did before. We consider the difference between this in time by using a time step h. We remember that this is the evaluation in time of a probability distributions over the paths. This allows us now to put inside here the corresponding evaluations at the particle level. We remember what does it mean somehow a change in terms of time with respect to the sigmas. We have to include now the replicator dynamics. And now we use a Taylor expansion, and the Taylor expansion is with respect both to x and sigma, so that this sort of gradient that we see here, it's a gradient with respect to space and a gradient with respect to the probability distributions over the strategies. And here again, the average field comes out integrated with respect to the corresponding sigma, and eventually we can again rewrite everything in terms of evaluation in time, and we end up with a transport equation for epsilon going for h going to 0, where the driving somehow transport field is given by a average transport field with respect to the mixed strategies and the replicator dynamics. So in synthesis, you have a very nice compact type of equation. And now if we restrict this equation to the first marginal, which is the distribution, how the distribution of agents is moving, you end up with this very nice purely transport equation with a certain vector field, and this vector field is what I call the mean of the mean. It means that, well, actually here there is a mistake. It should be it's a typo. So v of t is the integral of the integral over ex U the sigma U the pi sigma, where pi sigma times mu is the disintegration of the capital sigma with respect to the first marginal. Okay, and so what you are doing here, you are averaging the field, and you are averaging with respect to all the mixed strategies in the position X. Okay, that's what you are doing. So it's the mean of the mean. Okay, so now we have a truly nice transport equation, which is exactly what we wanted to have at the particle level. And so the question is, can we make a theory of well-posedness of these equations? Okay, so the theory of well-posedness of this equation is interesting because actually we are working on probability over probability space, an evolution there, and it is more involved, as I try to point out now in the next minutes, because of certain things that you are used to do in Euclidean spaces, and somehow in this setting is more difficult to be done. So now we are interested to characteristics of this evolution over the convex set, and in order to use somehow theory of ODE, Bochner, and Fréchet calculus in Banach spaces, we do embed C into a proper Banach space. So we try to look at this space actually as a convex set, a closed convex set into a Banach space. And the way we do it is by considering the span of the probabilities and closing it with respect to the dual topology with respect to the Lipschitz functions. And this is a space that is actually allowing us to, it's a separable Banach space, and as such somehow it's certain features that make it easier to play with respect to maybe embedding this into a non-separable Banach space, like the measures or something like that. So, by using that we can define a norm now on the space Y, and the space Y for us, it's not, it's exactly the cross space RD times F of U. So we are embedding P of U inside F, and that's the way we somehow look at these evolutions in a convex set within a Banach space. Okay, so within this framework, we can consider any evolution in this space, and we fix it. And by fixing it, we can consider the evolution of the corresponding characteristics, simply looking at the dynamics of each particle, where here now we consider the evolution not anymore in a stochastic sense, but is a sort of average player evolution. Okay, and here the corresponding replicator dynamics for one mixed strategies, and you can look at this as a ODE in the Banach space, that we are interested in. So, in order to show well-posedness of these evolutions, we are using a very classical theorem of Bretzis that tells you the following: if you have a suitable right-hand side field that is Lipschitz, at the same time is continuous with respect to the time, it has a certain property that basically it does not move you out of the set C if you just make a minimizing a sort of Euler type of scheme. You don't get out of the convex set C. Then basically the corresponding evolution of this type it's remaining as a curve in this convex set C. It is going to be of class C1 in the Frechet sense, and at the same time is going to be it is going to be stable with respect to the initial conditions. So the fact to have embedded everything into a Banach space gives you for free a certain type of well-posedness at the level of the characteristics and stability and all the features you want. Of course, you have to require a certain regularity in order to have this classical theory and so on. Okay, this allows you to define a flow map. So what you know is that for every sigma, you will have a transition map induced by this kind of ODE. And therefore, now you do have this flow map. And by using that, you can transport any initial probability distribution and by push forward by means of the map, and by taking any function that is sufficiently smooth, you can prove that this corresponding probability distribution is going to solve a certain PDE in the weak sense. And this PDE in the weak sense, it's of course depending on the particular sigma that you selected here to evolve the characteristics, and this allows you to define a notion of solution, which is a solution that is self-transported as usual. So in a certain sense, you would like to have here that the sigma hat is exactly sigma itself, and this gives you two definitions of possible solution. The first definition of solution is say that sigma is an Eulerian solution for the equation that we saw at the beginning, if somehow this relationship holds for sigma hat equal to sigma. Instead, we say that sigma is a Lagrangian solution if it is corresponding really to a fixed point of the transport type of equivalence by push forward of the characteristic along the characteristics. And why we are distinguishing the two notions? Because so by this construction we see that somehow the notion of solution in the sense of Lagrangian sense is actually an Eulerian solution. But what will be the issue is that the uniqueness of these solutions will not imply the uniqueness of Eulerian solution in general. So, and the reason is that the following. So Lagrangian solution are Eulerian, and this in a certain sense clarify that if you prove existence for Lagrangian, you prove an existence for Eulerian. But if you prove uniqueness of Lagrangian, the uniqueness of Eulerian will be left open. And the reason is that differently from Euclidean domains, Y is a separable Banach space, and there is potential lack of density of tensor product functions of smooth functions in the space C0 0t times y. So it's not obvious. So in Euclidean space, you can, in a certain sense, approximate continuous function by tensor products, and this cannot be done in general whenever you have a general Banach space. And so, and the reason is that on the Euclidean space you have polynomials that you can use, and here not. And so the two notions are not obviously true. Moreover, approximation by smooth functions, you can do it on the Euclidean space because you have convolution kernels, and here you don't have convolution kernels. I mean, you cannot do smoothing by convolutions in general. So somehow you have some hardness in the density that allows you to pass from one notion of solution to the other one. So the existence and uniqueness of Lagrangian solutions, well, it goes more or less in the solution in the sense of fixed point of this kind of equation, goes along the lines of the proof that one do for transport equations on Euclidean spaces. It's very much similar, given the fact that we have the existence and uniqueness of characteristics. So the idea is that you first try to prove, so this is the theorem, so it exists. There exists a unique Lagrangian solution, moreover is stable with respect to the Wasserstein distance. And of course you want to restrict everything to P1, where somehow 1 represent the measures somehow that are have the first moment bounded with respect to the variable x. Okay, now we are assuming that U is a compact set, so we are not really considering moments in that direction. The proof follows from the stability of flow maps, which is something that comes from the Brezi's theorem with respect to the Wasserstein distance. So in particular, what you can prove is that somehow once you have the stability of the flow map, this is transported to stability in the sense of the corresponding probability distribution that define it, and what you have is that the distance of with respect to the Wasserstein distance with respect to these two evolutions will be bounded by the Wasserstein distance, and if you introduce now a distance that is discounting in time the Wasserstein distance of the two lambda t prime, somehow what you end up is in a contraction principle that allows you to say that this equation has a unique fixed point, and in this kind of stabilities will give you also this kind of dependence from the initial conditions, and this is the way you prove existence and uniqueness of Lagrangian solutions. The uniqueness of Lagrangian solution, you can approach it in two ways. One way is through a duality principle, and so now you assume that J and the vector field E are both Lipschitz, as you did it before. You have to ask, though, that they are a little bit more smooth to use this technique, so that you need that they have a certain, in certain directions, they are actually of class C1. And then you can show that there is a uniqueness of the Eulerian solution in a space of actually signed measures that are bounded, that is a first moment bounded of the total variation. So in a certain sense, paying a little bit of price of smoothness, you gain the fact that you have a broader sense of uniqueness. And the way you do it is by duality, but in order to do that, you need to introduce a new notion of distance. And the new notion of distance in a separable Banach space is the suprema over the C1 functions which are bounded. At the same time, they have bounded Lipschitz constant. And this define a new distance that whenever you restrict it to the space of probabilities with the first moment bounded, then somehow what you get here is precisely the Wasserstein distance. The proof of this is more or less as follows. The symmetry and triangle inequality are easy. The non-degeneracity of this distance that tells you that if the distance between two measures is 0, then the two measures need to be equal, follows from the equivalence between the Borel sigma algebra and the sigma algebra generated by cylindrical function. which are actually admissible by rescaling, are kind of admissible competitors within this soup. And the way to prove that these actually coincide, and so whenever you have a zero of two measures, then they need to coincide on the sigma algebra or cylindrical function, but this Bode sigma algebra is equal to the cylindrical sigma algebra, but of course this has to be done in separable Banach spaces, so this equivalence hold only there. And whenever somehow you want to check that this distance is equal to the Wasserstein distance with P1, well, it follows from not from the fact that you can approximate Lipschitz function by using C1 function, because this thing cannot be done there, because you don't have convolutional kernels that can allow you to smooth functions and approximate it in this sense, but it comes from a closure of the problem with respect to the pointwise distance. So in a certain sense, you can resume this equivalence in the terms of soup and in terms of closure with respect to the pointwise distance, and without invoking the necessity of a smoothing of the functions and so on. So that's the way you do it. Okay. Now we have this tool at disposal that will come out naturally in the proof of uniqueness. So we consider the difference between two solutions that starts from the same probability distribution, and they solve this corresponding equation where here we have a very special vector field, which is the difference with respect to the vector fields of the two solutions, and we consider a backward transport with respect to a given right-hand side that is C1 bounded. And we know that an explicit solution can be expressed in these terms, where here we have the flow map with respect to the sigma 1 that is appearing here in this vector field B. And this can be proven under smoothness assumption of R. So R is supposed to be C1 bounded, and also we need to do a sort of a sensitivity analysis of the y's with respect to the initial conditions, and you want that also this is smooth with respect to the initial condition in a suitable sense. And by considering these two equations and pairing them, now you can basically consider the following set of equalities that allows you, in a certain sense, to extract information here. So you know that this term is actually equal to R, and so by bringing this on the other side, you get that R times sigma t is always bounded above by this term. We know that the supremum with respect to R of this term is exactly the distance that we introduced before. And by doing suitable computations and here and estimates taking into account Lipschitz properties that we have in the fields and so on, you get up here that everything is scaling in the following way. So for h sufficiently small, you know that the two probability curves, the two curves needs to coincide on this interval, and by consider further interval, you can extend uniqueness to the entire interval in time. Okay. This is one way to prove the uniqueness. There would be another way that allows you not to require all the smoothness that we have here. It would go through a superposition principle somehow for ODEs in separable Banach spaces. For the sake of time, I try to skip this part, but let me show you one application. So what about equilibria? This is a very quick thing that I show you just to have your understanding that this can be applied and can be used in practice. So let's assume that we want to minimize a mildly smooth but certainly non-convex function, which is usually a very difficult problem to find global minimizers. And the problem is that can we design an evolutionary game, a non-homogeneous evolutionary game of n players that can converge to one global minimizer? Well, the idea is that you choose somehow a potential, a payoff functional that, in a certain sense, tell to one particle that is more convenient to move towards another particle only if the other particle has a better value of the function g. And by counting more those particles that have in this interaction potential, by counting slightly more particles that have a smaller value of the function, then you have a game where the particles tend to go in the direction of those particles that have a smaller value of the function g. What actually you are computing here is essentially a non-local gradient of the lowest semi-continuous envelope, convex envelope of the function g. And this is the kind of results that you get. So these are the probability distribution of each particle that starts centered and then they adjust. And everybody eventually converges to the global minimizer in a nice way. Of course, you can consider much more complicated functions that have a zillions of local minimizers, but still you end up with the global minimizers. Even here, there are even more local minimizers, but they don't see it. They simply fall there. And here you have also some local minimizers that can fool somehow the system. And here you add diffusion, which means that not only moving stochastically with respect to the strategies, but adding additionally a little bit of Brownian motion, you see that the particles can really start all together very, very far away, but still somehow in due time, they kind of sense the presence of the global minimizer, and eventually they converge to an equilibrium of the game, which correspond actually to the minimizer of the global function. Okay, so I thank you for your attention. Sorry for being a bit longer. And
So you somehow have a decoupled dynamics in the sense that the strategies are just transported along the particle trajectories. In a true evolutionary game, you may imagine that the strategy itself evolves along the path of particles. Would you be able to include that possibility?
they are decoupled. What does it mean?
Decoupled, I mean that if there is an agent with a strategy, then this strategy just carried over where the agents will go or distribute. But the strategy itself for the agent do not evolve. Am I right?
Well, if you are in a position, so in a certain position and with certain strategies, you will find agents that are distributed there. So which means that there are multiple agents that somehow, once they are in that position, will use that mixed strategy to move. And you have a certain amount of them. Mm-hmm. That's the way you have to understand it. Okay. In the numerics, you saw that actually in a certain position with a certain strategy, there is basically only one. agent that move in that sense. Okay, so that in a certain sense, for the particle dynamics, the initial interpretation that we gave correspond to the second interpretation. So on individual-based dynamics, it's hardly somehow two agents will be in exactly in the same position, and therefore somehow each of them will be an individual. But in the second modeling that we provide, you have to think that for every position and every mixed strategy, there is a distribution of agents that can be in that situation with that strategy. And when they move, when that agent move in a certain other position and and somehow its mixed strategy also move, and so it change its location within the entire distribution. I don't know whether that's clear.
Yes, but the strategy itself does not evolve. That's what I mean. So the strategy itself related to the agent does not evolve, while in evolutionary game, usually the strategy itself related to one agent
the strategy evolves. You change.
Evolves?
Yes.
Okay. All right.
It evolves. Okay.
Oh,
Okay.
okay, so I think it's time to thank Massimo again.
Yeah.
And now we Madison. And
Yep.
so the title is about graphs and optimal transportation, but it's really long.
Yeah, I will repeat the title again. Okay, so thank you for coming to this last day of talks, and well, to my talk. So as you can see here, it says Brown, but that was as of I don't know, 3-4 months ago. But now I'm in the University of Wisconsin-Madison, so I have to be faithful to my current institution. So I have to clarify that. So today, I'm going to present kind of like, to some extent related to what you saw in Marco Couturi's talk, where you have optimal transport playing a role in trendy and current topics of interest in science in general and in engineering. But I'm going to do it from a different point of view. So instead of like being more concerned about methodology, I'm going to be more concerned about how ideas from optimal transport can help us proving theorems related to procedures that people use in machine learning. Okay, so that's going to be somehow what gives meaning to this title. And so let me just kind of briefly give you some hint of what is the setup and what are the types of problems that people consider in machine learning, maybe some terminology. So the idea is you're given a set of data points, and then you're going to use that set of data points to learn from them. And so here what I'm showing you is essentially like a simple arrow taking points into some procedure that depends on those points that you observe. And the points can be, in principle, anything that you want. So here I just pick paintings because I like them. And so the idea, for example, could be, like one possible question that you may ask is, just by looking at the data points and without any other information, you would like to understand what is the meaningful groups within a data set. Okay, so no one is telling you what these paintings are or who painted them, yet you want to uncover a structure. So for example, you would like to say that there is some paintings that are more similar to each other than to other paintings. In this case, the Velázquez painting should be more similar than, I don't know, Giotto's paintings or something like that. And so then that's just the usual unsupervised learning problem where no one is telling you labels, no one is telling you anything, you just have to uncover the structure on your own. But maybe you have an artist friend who labels some of these paintings for you. So maybe this painter gives you some labels for some of these paintings, and now maybe you would like to also use that information to better understand the underlying structure, in particular be able to classify other paintings. So maybe someone is telling you that this is Velasquez and so on, and then you would like to use that information to later classify other things. Okay, and so then that would be the context of supervised learning, and if you only have partial labels, then people talk about semi-supervised learning. Now, the talk, so just to say, of course, like paintings is one thing, but of course you can imagine more relevant applications for science and medicine and so on. There could be steps in between. So usually, you receive the data in the form of, say, images, but maybe to better process the data, you may use some transformation to make it more manageable. Anyway, so just from the mathematical point of view, and just to tell you what the results I'm going to present today are about, I'm going to be imagining the situation where, the statistical situation where I think of these data points as samples from some distribution. And for the most of my talk, I'm going to be imagining that these are IID samples, although I will comment on, the fact that that's not necessarily that relevant. But I'm going to be imagining that although these data points may live in a high-dimensional ambient space, like think of images and think of the space as being grayscale on all the pixels or something like this, we still are going to imagine that nonetheless those the support of that measure, the measure of the data, actually is lower dimensional manifold in this ambient space. Okay, so I'm going to be imagining that support is M, and I'm going to be thinking of M as an M-dimensional manifold, and M is much, much smaller than D. Okay, and I'm going to think that distribution has a density on that manifold. And so I have the data, then I have some procedure, clustering or classification, and so on. And it could be, that procedure is partition the data into meaningful groups, clustering. Or it could be, if in addition you have labels, then it could be, the procedure could be find a classifier. Just give labels to all data points and perhaps even to examples that you haven't observed yet. And the question is, in this day and age where we're talking about big data, large data sets, I think it's pretty meaningful to ask what happens as you get more and more data points and what these procedures are looking like, and how can you use that information of limiting procedures in order to produce better algorithms, better behaved algorithms for large number of, although finite, large number of data points. Okay, so this is the talk about. And there is a large class, of course, of procedures. People have many approaches to do learning, but I'm going to be focusing today on graph-based learning. Okay, so it's going to be learning that is based on a graph structure that you put on top of the data points to try to extract geometry from the cloud. Okay, and I'm going to give you 3 examples of these graph-based learning approaches. So the first 2 are about clustering, so unsupervised learning, and the last one is going to be about semi-supervised learning when you have where you have labels. And I'm going to, for those of you who do statistics and know about Bayesian statistics, so I'm going to give a version of Bayesian semi-supervised learning, and I'll explain why one would be interested in something like that and so on. So along the way, I'm going to make comments about extensions, problems, and of course, if time permits, I'll elaborate more on some of these examples. But these 3 things are going to be kind of like toy models to give you a sense of what is the type of work that I do. And in a sense, all of this is just like a program that started around 4 or 5 years ago when I was a PhD student in Carnegie Mellon. And with my advisor, Diana Slepchev, at that point, we started working on these types of problems. Okay, so I just want to mention that this type of questions of large sample asymptotics of procedures, in a sense, has been studied in the past by people in the machine learning literature, but somehow the methods that I'm going to be showing you, which related to the topic of this workshop, are quite different from their methods, and also in terms of results, the results are quite different and perhaps more powerful, the ones that I'm going to present today. Okay, so let's start with the first example, so clustering based on graph cuts. So just the toy model is going to be like this. So I have my point cloud. That point cloud is supported on the manifold M. And my goal is to find meaningful partition of the manifold into two sets, just toy model. And so I said that this was going to be defined in terms of a graph, but I haven't introduced yet the graph. So I have the data cloud, and I'm going to be imagining that I give weights to pairs of points. These weights depend on essentially two things. First of all, one parameter, epsilon, that is controlling data connectivity. So that's something that the user picks. And also something that the user picks is a non-increasing kernel. And the idea is that essentially, roughly speaking, you're going to have weights that are higher for points that are closer than for points that are farther away. And closer here is the measure with respect to epsilon. Here I have the Euclidean distance. It's important to be the Euclidean distance because I don't know what the manifold is. I only see the ambient space. So the only thing that you can do is measure Euclidean distance or some sort of ambient space distance on that space, but not the geodesic distance. A typical example is just a kernel that is, connect if points are within distance epsilon, don't connect if the distance is higher, so a kernel like this. And at least for the cloud that I showed you before, a graph with that kernel for a given choice, given a choice of epsilon would look something like that. Now let's just see how we can define meaningful partition into two sets for a data cloud. So I'm going to do it via a variational problem. So I'm going to say, well, I'm going to be interested in a functional that looks like this. It's a quotient of two things. The numerator, is going to be a cut functional. The role of it is just to measure interfaces between sets in the cloud. So basically what you do is just count how many edges there are between one set and its complement. And you can call that a graph perimeter. You can rewrite it in this way, up to a scale of 2. And, well, written in this way, this looks more like a total variation of an indicator function. The denominator is there because you want to force partitions to be balanced. You don't want to have a partition into all points except one, because that's not meaningful. So that's why you put something like this. And then you say, well, just mathematically, let's forget for a moment about the computational aspect. At least mathematically, let's just consider the minimization of a problem like that. Okay, so that's a Chigger cut. And then we would denote the A n star complement, the M minimizer of this functional. And in the language of procedures that you construct from data, well, here the procedure is give me a data cloud and I give you this A n star complement. This is my partition. So then, okay, the picture for the graph that I showed you earlier, the minimizer would look something like this. The one of the sets is, say, the white dots. The complement is the dark dots. And then the observation is as follows. The observation is, well, for a good choice of epsilon. So I picked some value of epsilon over here, and I got this picture. And then at least visually speaking, I would say that partition resembles a partition, an imaginary partition that you would be making in the manifold. And I'm going to be calling this partition A star complement. And I'm putting there the stars because, well, you can imagine that those are minimizers of an energy now, that now you define at the continuum level, where now the numerator is going to be a total variation. And at least for a smooth sets with a smooth boundary would have some like surface area taking into account the density. Okay, if you want to generalize for more sets, then you would have to put the essential boundary, or I forget the name right now, but anyway, so for smooth sets it would look like this. And then the picture, we would have discrete world on the left-hand side, continuum world on the right-hand side. You have a variational problem, discrete, variational problem, continuum level, a minimizer, two pictures, and then the question is, okay, well, as n goes to infinity, does this procedure converge to that procedure over there? Okay, but there are two questions, and I think mathematically, at least, the first question is in what sense we're making sense of this convergence, if there is such a convergence. And more importantly, and this is perhaps mathematically it's important and attached to the first question, but for practitioners it's also important to understand the scaling for these constructions. So you have to understand that if the parameter epsilon is too small, then the graph becomes too disconnected and it's not going to be revealing the geometry of the data set. But if the parameter epsilon is too large, then you may run into a situation where you have a very dense graph, which is computationally speaking more involved to work with, or more difficult to work with. So there should be like some understanding of how big you need epsilon to be able to recover the geometry that you want. So let me say that for most of the works that try to study the passage to the limit of variation of problems at a discrete level towards a continuum level, like the typical topology that people use is to think of like for any given discrete function, you extend via Voronoi extensions. This is kind of like the canonical way to do it. And for some reasons, and perhaps I'll mention that later, in machine learning that would be quite useful, because Voronoi extensions, you just need the points to define them. So if you give me another point, I would automatically be able to associate a value to an external point. So Voronoi cells you can construct right away, only looking at the point cloud, but mathematically it's actually for this problem it's quite difficult to work with. So this is not going to be the topology that I'm going to be using. It's not going to be the one coming from these Voronoi extensions, but rather something that comes from transport. And this is part of the reasons why this talk is related to the workshop. And so the idea is to really view these discrete objects, these discrete indicator functions, or these discrete functions, and also the continuum counterparts as elements of the same space. And so at least intuitively, this picture explains what is the structure that we're thinking of. And the structure is more or less like this. So you may have like an indicator function for a discrete set. This is UN. You may have an indicator function for a set at the continuum level. This is U. And each of these functions is attached to a measure, a base measure. On the one hand, you have the empirical measure for your data. And on the other hand, you have the measure that you use to produce the data. And so I'm thinking that these elements, like the discrete function and the continuum function, are actually part of the same space, but provided that you interpret UN not just as UN on its own, but as UN coupled with gamma n. Okay? So formally speaking, this TL1 space is just a pair where you specify a measure on your manifold, and once you have specified the measure, you define a function on the L1 space associated to that, and then on top of that you put a transport distance. Okay, so this TL1 space is really just a subset of the space of probability measures on the product space, where you have manifold cross the real line. But there are some benefits of looking at TL1 on its own, okay, and it makes more transparent the topology that one is using to compare these variational problems. But both interpretations are quite useful. Anyway, so this is the metric space where I'm looking at these functions, and they are part of the same space. Also, then I can interpret the functionals, the cut functional at the discrete level and cut functional at the continuum level. Now I can view them, both of them, as functionals that I'm defining on this metric space. But then with that definition of the metric space, then I can give you a theorem already. I can tell you when you have convergence of the discrete minimizers on random geometric graphs towards continuum minimizers. Okay, so essentially your scaling for your graph has to scale in a certain way, But provided that it scales in a certain way, then with probability 1, you have the guarantee that in that sense that I described earlier, you have the convergence of the discrete solutions towards the continuous solutions. Okay. So now let me just give you, a sense of what is happening here. What are these scalings? And by the way, this is, I'll comment on the optimality of this scaling in a moment. But for now, let me just tell you where or what this scaling is. So actually, this is related to Michel's talk yesterday. Well, he discussed the scalings for empirical measures and ground truth measures, but looking at p cost. Here I'm looking at infinity cost. As in the case of p cost, there is a transition. What happens with dimension 2 and what happens with dimension greater than 2. But if you remember, and I don't know if you remember the scalings, there was something like 1/2 over here for m equals 2, and there was something different for m greater than 3. Well, here, you still have like this transition between 2 and 3, but the scalings are different. And the problem is quite different, the infinity cost, because you may also remember, at least for the p equals 2 case, you essentially would have like a universal constant, for the scalings when you look at compact manifolds. For the infinity cost, that's not going to happen, and it's not bound to happen, because you may imagine a situation where you start with a ball, you shrink it towards the middle, you make it narrower and narrower until you separate things. Once you have a disconnected manifold, there's no way that you're going to have convergence towards 0 of the infinity cost. Because essentially, as soon as you have discrepancy of one measure with the other, then immediately you would have to travel something of order 1 to do the matching. So this infinity cost behaves quite different from the other costs. And so in the 80s and 90s, these same people that Michel Leduc mentioned yesterday, they also obtained kind of estimates for this infinity cost, but in the case of the cube. Okay, so the uniform measure and a uniform cube. But of course, if you wanted to extend this to other manifolds, to other densities, it doesn't follow straight in a straightforward way. You have to do a little bit more work. So we generalize with Day and those results. It's not extremely difficult, but and this was just a technical tool that we needed, like concrete estimates on how this behaved. But once one has concrete estimates for how this behaves, one can plug in those in here. So whatever we would have obtained, we could have put over here. And so what that means is that essentially the proof for this theorem that appears here doesn't really depend too much on the IID structure, only depends on the infinity cost of some empirical measure with the ground truth measure. So that's good news and bad news. Let me just give you the good news. The good news is that then this theorem would apply for more general structures for point clouds, so not just IID. You can even imagine sequential, you receive the data in a sequential form. If you give me an estimate of what this infinity cost is, then you would have a theorem like this as well. So that's good news in that sense. I shouldn't say this for this audience, but just to give you like the logic behind all these constructions are as follows. So we have a metric space. In this case, it's going to be TL1. We have a sequence of functionals. This one's over here. We have a notion of convergence of functionals that guarantees the convergence of minimizers. For most of the audiences I give this talk to, I would have to explain it like this, but for you it doesn't really matter. But I guess what is important here to understand is that for the machine learning community, neither optimal transport nor gamma convergence was the usual tool to use. And I think that what was important from our work was to really put together all these tools in a way that you could obtain convergence results that were unavailable thus far. So essentially, that was the step, the crucial step in that program that we started was a paper that we wrote 3-4 years ago where we essentially study the gamma convergence of the graph total variation towards the total variation. And then, okay, for the Chigger functionals, you have the denominators are a little bit easier to handle. But that was the kind of crucial framework. And really, just to give you a sense of what was behind that, those results, so it was really, and where, for example, this infinity cost comes into play, is really like this game of playing with an intermediate energy. So on the one hand, we have a local total variation energy. We have the graph total variation, which is a kind of finite difference, but a sum. And then intermediate energy would be finite differences, but with integrals. And so, you know, in the past 10, 20 years, I would say, these non-local energies have been studied, and there are plenty of results establishing connections between non-local energies of this type and local energies like the total variation that I was mentioning earlier. But the infinity cost is really nice because you can relate pretty much directly this graph total variation with an energy like this after composition of map. And the way it works is just you look at the change of variables, you look at what is the error that you're making when you change variables here, and if you make sure that your parameter epsilon is larger than the infinity cost, like how much mass is moving, then you have essentially an inequality, an asymptotic inequality relating this guy with this guy and vice versa. You just have to play with this scaling. So it gives you like a very simple proof once you have the right tools in hand, so the proof should come out easily. So it is more or less like that, the philosophy. Okay, so that was the first example that I wanted to show. I'm going to show you now another example in clustering. So now let's forget about graph cuts. Let me now look into a similar problem. Now is suppose that we're going to do a partition into k sets, not just two. So traditionally, what people do to do this, or in the graph-based approach, what people do is use the graph Laplacian. So the graph Laplacian would be a matrix that looks something like this. It has its eigenvalues, eigenvectors. It's a symmetric, positive, semi-definite matrix. Then you can, well, it has a, Dirichlet energy associated to it. And then you can define this spectral clustering algorithm that goes like this. You have your data set. You find the first k. So you map the data set to Rk. And the way that you produce that embedding, so each data point is mapped to a vector, you'll do that by evaluating the first k eigenfunctions of the Laplacian. Okay, so each of these UIs is an eigenfunction for the graph Laplacian. And once you have in this, you have embedded the data like this, then you do something like k-means. Okay, so here I just wanted to mention, the philosophy behind doing this embedding, and in a sense, why do you use graphs and not go directly from here to here and do k-means directly, is really because you want to be able to handle situations where your data set is not necessarily Euclideanly arranged. So if your data set was something like this, like in a weird spiral form, and if you were trying to do k-means in something like this, then you would be trying to cut like vertically, assuming that data set looks like a ball, rather than like what is intrinsic to it, which is a spiral. So somehow this idea of these embeddings is to try to entangle those types of data sets. Okay, so you have a continuum version of that. You would have like a differential operator. You have eigenvalues, eigenvectors, or eigenfunctions. And then you have a picture like this. This is the discrete world, the continuum world. Then you can ask the same question as before, what happens as n goes to infinity? Same proof essentially would give you the passage to the limit of this partitioning towards this partitioning over here. But at least in the spectral case, you can say more. You can give rates of convergence. You can say not only how, that you have asymptotic convergence with probability 1, but you also have rates. And in particular, you can relate the spectrum of the graph Laplacian to the spectrum of the continuum Laplacian in this form. So here we have the epsilon is the connectivity length scale for the graph. Delta n is that infinity cost that appears over there. And okay, so these estimates actually, they are obtained, these quantitative estimates are obtained kind of using similar ideas as in a paper by Burago, Ivanov, and Kurilev, where they use kind of like this very carefully designed discretization and interpolation maps where you can relate the Dirichlet forms of these two operators, one at the discrete level and one at the continuum level. And so that allows you, this discretization interpolation maps allow you to, as I was saying, relate these Dirichlet energies in some way. You would have in between, like again, this non-local object. You would be more careful than the asymptotic analysis that we did for all the other functionals. But the bottom line is that one can obtain estimates like that. Now the truth here is that these estimates are not optimal. In fact, the optimality, one would expect that this depends like epsilon, but you see, you have to make epsilon appears in the denominator here. So the best thing you can expect is the rate would be like a square root of what is appearing over here, which is not optimal. But the good news is that this is kind of like you can bootstrap these results, and using other techniques more related to PD-based tools, you can actually get to the optimal convergence rate. So that's good news, but this is something that is still in preparation. Nonetheless, I may say that as of right now, these types of estimates are state of the art. But what I'm trying to say is that even if you don't like that proof, they can be used to be extended to quite optimal results. Okay, I can skip this just in the interest of time. So now let me move to give you the third type of scheme or task that I'm interested in. So now I'm going to introduce the labels. And I'm going to be imagining that I have n is very large, whereas p is quite small. Actually think of it as something fixed. So I have some labels for my data set. And I would like to be able to extend those labels to the whole data set, not just to the first p that were given to me, but of course to everyone else. So typical approach would be to introduce, you have some regularization term, so that's not to commit overfitting, which is kind of the term that people use in machine learning or statistics. And then also fidelity, so that you match with the labels that you do have. So, if you were just interested in finding a point estimate of what should be the classifier or the regressor for the other points, you can solve this minimization problem. But if you're interested in also telling or giving information as to how certain you're about your inference, then you should introduce perhaps a little bit more sophisticated tool. So in particular, we would like to have a notion of uncertainty quantification of the classification that you do. So in a recent paper by Andrea Bertozzi and collaborators, Andrew Stewart, they introduced this framework where they say, well, you think of your classifier or regressor, what you're trying to learn, actually as a random variable. And that random variable is some Gaussian with covariance matrix, some power of the graph Laplacian. And you have a model for how the labels are obtained once you have specified the classifier. And then you introduce this posterior distribution that tells you, given the observations, what can you say about the classifier regressor that you're trying to recover. So, okay, so that has a form like this. And in the Bayesian statistics, this is just a Bayes rule. You have a prior on the unknown. You have the model for your data given the unknown. And then what you're interested in is what is the distribution of the unknown given what you observe. You can imagine then that there is a continuum counterpart where now you have functions defined on your manifold. You have a prior on that known on the manifold. In this case, it would be a Gaussian process in the manifold with some covariance operator related to the Laplace-Beltrami operator, and you would have a posterior, distribution on functions. And so again, one would be interested in the large sample asymptotics. What happens as n goes to infinity? In what sense? How should you scale the epsilon, and so on? here the question, one needs like to extend things, because of course now we're interested in distributions of functions. So then if we recall this TL2 space, the idea was to embed spaces of functions at discrete and continuum level into like a common space. So now if we're interested in the distributions of these guys, well, the natural thing to do is, well, those maps, those embeddings that I showed before, canonically induce like embeddings at the level of distributions. So now it makes sense to say, well, if I have a posterior for discrete functions and I have a posterior for continuum functions, then it makes sense to talk about this guy converging to this guy in the, for example, weak sense in the space of probability measures on the metric space TL2, or Wasserstein space on the space of probability measures on TL2, things like that. Okay, so this is just the main idea. Oops. Okay, and so then in that respect, then there is a similar result to the ones that I showed previously. So basically, you have consistency at the level of the posteriors. There are some differences in the scalings. In particular, there is an upper bound here that depends on the exponent that you have on your graph Laplacian. And this is crucial because if the exponent is not large enough, then you don't even have a well-defined measure in the limit. You don't have well-postness. But putting aside those important issues, the main moral is that you would have convergence at the level of the posteriors. Main ideas, one can also use ideas from gamma convergence. Now, viewing posteriors, traditionally in statistics, people think of them as a Bayes rule, but I think a more convenient way to think of them is actually as solutions to optimization problems. And perhaps for a mathematician, this would be quite a natural way to look at it. But once you have the right framework, then you can pass the limit. Now, let me say one thing about going back to this graph Laplacian versus the continuum Laplacian picture. So when you plot, for example, the graph of the spectrum of a sphere, like two-dimensional sphere, and you compare to the spectrum of the graph Laplacian that you construct with IID samples on the sphere, you would see a picture like this. The blue one is the graph Laplacian, the red one is the true Laplacian. And one thing that you can notice is that there is some plateauing at some point. There's some threshold. So this is the index of the eigenvalue that you're looking at. This is the value of the eigenvalue. And there is some plateauing at some point. There's some transitioning. So that can be explained, from those estimates that I showed before. So when you look at this, the error of approximation of graph Laplacian versus continuum Laplacian, it depends in this way. And then there is this term square root of lambda I that appears in the epsilon over there. So of course, for this to be small, then this guy should be small, and in particular, this guy should be small. But you have some understanding of how this lambda I grows, which will tell you that this approximation is going to be fine, provided that you're looking at indices that are smaller than this transition here. So actually, with other methods, you can establish that somehow this is more or less, this is the scaling at which you would see that plateauing. But that form of, analytical information is useful, because then you would say, well, if people use these graph Laplacians for regularization or for clustering, why do they care about the whole spectrum? If at the end of the day, there is part of the spectrum that is not giving geometric information after some point. So then you can throw away some of those eigenvalues and that part of the spectrum, just focus on the first part. You would have exactly where that transition should happen. And so in particular, you can consider all your inferential procedures just based on truncated versions of the Laplacian. Okay, so this is kind of like, this result would be saying like, oh, if you remember there was a constraint on the epsilon, well, if you remove those bad eigenmodes, then you go back to kind of the usual setting where you have a higher range of possible values of epsilon that still would give you consistency. So this is what I'm saying here. So here this would be the truncated prior. You don't keep all the modes. Now let me tell you a little bit of how somehow this consistency theory, like, okay, so this is just, so far what I've shown you are theorems that tell you what happens as n goes to infinity, some rates of convergence, some choice of parameters, some information that is useful for practitioners and so on. But now let me tell you how somehow understanding the limiting object, how understanding that your procedures are well posed, can help in designing schemes that are well behaved in the large N setting. So in this paper, in the same paper that were of Bertozzi and collaborators, where they introduced this Bayesian approach to semi-supervised learning using graph methods, they also propose an algorithm, like a Markov chain algorithm to Monte Carlo Markov chain algorithm to sample from that posterior. Okay, so so they propose something like this. They say, well, they're going to construct a sequence of classifiers, say, that are generated randomly according to a Metropolis Hastings type scheme, where you have a proposal step where kind of the novelty compared to what traditionally was done was introduce this kind of a damping term, 1 minus beta squared, which with beta strictly less than 1, so that this number is strictly less than 1. So it's like a random walk, but then you're shrinking. And then, okay, you have some accept reject a step that looks like this. In particular, it doesn't depend on the prior, only on the likelihood. So they propose this scheme. And the reason why they propose this scheme is because earlier, Andrew Stewart with collaborators, they had proposed a Markov chain that now is in infinite dimensional space, which can be proved to be well posed. So this algorithm is well defined. So this is a Markov chain that makes sense in infinite dimensional space, and also is robust to discretization of the form truncating the eigenmodes of the continuum prior, the continuum Gaussian field. So this is because these people in particular, Andrew Stewart, so they were interested in doing Bayesian formulation of inverse problems. And so they needed schemes where you discretize a PDE, you discretize a forward model, and then you would like your algorithm to be insensitive to discretization. So that's one form of discretization, the one that would come from numerical analysis. But the whole thing is that actually what we are doing is a form of discretization of the PDE. It's just a different form. And so it makes sense then to try to connect the scheme that you would do for data, which you can think of as a discretization of a continuum object. And then what turns out is that the well-posedness of this continuum object that we understood from our theory somehow is going to induce and can be proved to induce well behavior at the level, at the discrete level. In other words, that as n goes to infinity, the Markov chains are not going to deteriorate. In particular, you can talk about uniform spectral gaps. This is one way to measure, for example, in terms of the computational cost, just one way to measure more or less how many steps you need to take in your Markov chain to be able to converge to the distribution you're trying to sample from. Okay, so somehow this result somehow would say, well, this is insensitive to some extent to the number of data points that you have. But this is only possible because you know the existence of this continuum limit. You know that people have worked for a long time in designing these schemes. And now you say, well, but if we interpret these random objects as a type of discretization of those guys, then probably they should inherit some of those properties. Okay, so that's somehow the main philosophy here. So let me then just conclude by saying that this program is intended to address statistical consistency of schemes that are used to learn from data. That the analysis usually comes together with the scaling of the parameters, rates of convergence, and so on. But that it also can be used for computational and algorithmic implications. So 2 years ago, so if you wanted to do something like Bayesian approach to this, people would use other sampling schemes that are not guaranteed to be stable. You don't know the properties of those schemes. So this is just a kind of an illustration of how can this analysis provide such implications. Okay, and so just to conclude, let me mention, kind of going back to this first result that I presented. So the result would, let's say, something like this. Was recently in past summer in a work by Matthew Penrose and Mueller, they actually show that the m equals 2 case can be improved. So in fact, it's not necessary to put 3/4 there. You can put 1/2, as you would expect. And the reason why you would expect that is because actually with those scalings, that lower bound coincides with the connectivity threshold for the graph. So below that threshold, you know that you cannot recover the Jigger constants. So somehow there was still this question of what happens with the 3/4. There is a gap between 1/2 and 3/4 there. So it turns out that you can do to go all the way to 1/2. But then what is interesting from this work is that they use, they try to analyze to some extent, the regularity of the discrete solutions. Okay, so now there is this kind of like opening of new directions where you would like to understand regularity of discrete solutions, which you expect that they are inheriting some sort of regularity coming from the continuum objects. And, but let me say one more thing. So since this paper, then we, together with Dayan and other collaborators, we were able to also obtain this result, to improve the case m is equal to 2, without using the infinity transport cost. So other method proof is more complicated, but still one can get rid of the this constraint and the use of the infinity transport cost, and it just uses basic concentration inequalities of the binomial type. Okay, so I think with that, I just wanted to, finish by pointing to some of the works, so many of the works that have appeared kind of like following this direction of using PDE tools, calculus operations tools, optimal transport tools to give analysis on this machine learning task. So we have work on clustering, different methods of clustering. We have approaches to classification, understanding of what is overfitting in an analytical sense, P-Laplacian regularization. And the list continues. This is a field that is growing, very fast, and well, I'm very excited to be able to tell you about it. And so I thank you for your attention.
In the applications to imaging, probably the dimension D is much larger than N typically. Mm-hmm. So if I think of pixels. Mm-hmm. So how would the first part of what you're doing perform if it's just about kind of distinguishing between a black rectangle and a black triangle, which are shifted and rotated? So that would be, I guess, a disconnected three-dimensional space. So M would be equal to 3. But perhaps the kind of Euclidean distance on the ambient space is not the right distance. So have you kind of checked some more or less toy but problems of this type?
Yeah. So then the question is actually quite appropriate, because so you could say, here I just presented the Euclidean distance, right? So points you connect. You think of images as connected by depending on the ambient space distance. And in that example that you're suggesting, like, your images are rotated, so probably Euclidean distance is not the best. You would like to think of that as just kind of like isometric to like a ring or something like this. So there are, that on itself is an important question, not just for my work, but in general. Like, how do you give, at the end of the day, how do you give feature vectors to your data points, right? So in a sense, the first step there, if you wanted to take an approach like this, would be to first do some sort of embedding. And then after you have done this embedding, then perhaps use the Euclidean distance. And for a long time, that was the way people would do this. Like first find the embedding, and then once you have the embedded space, and do the Euclidean distance. But if you look nowadays to this deep neural network, which is difficult to understand, so that kind of a step of the embedding is kind of hidden in all these layers. And at the end of the day, you get accurate results and so on. But I would say that if you want to do something more principled, then in principle you would need to first find the right embedding for your data, find the right description of how you want to represent your vectors, because otherwise, then I agree, you're not going to recover the right structure of the data set. I think in general it's a question for the field, not so much for the work. But yeah.
In the second approach, you suggested that applying the k-means directly is not going to work, but instead, if you first evaluate it in the first k eigenfunctions, it might work better. Do you have any intuition behind this?
Yeah. So, I guess this is related again with the idea of first embedding your. So, I mean, in fact, the questions can be connected, at least in that specific setting that you're describing. So, for example, here, if you do something Euclidean, then, and if you're trying to partition this spiral into two meaningful sets, and you do everything Euclidean, you don't look at the graph and so on, then k-means would pick something like, well, this is one set, this is the other. But effectively, what I would like to unravel is the intrinsic geometry of the spiral, which is essentially like a line segment, but just entangled. So now what happens is that when you look at the spectrum of the graph Laplacian, so you can imagine that the graph is essentially trying to replicate a line that is curved. So the intrinsic geometry is just what you would have for a segment. So for example, if you pick the first non-trivial eigenvector, you would expect that it would depend like this. As you move from here to here, it would transition from something that is positive to something that is negative. And so if you embed the data into like the first eigenvector, which is constant, let's say 1, and the second eigenvector that is this guy over here, and so every point xi is going to something like that, and what you're going to obtain is essentially the data points are going to look like this. Okay, so this would be the embedding that you would obtain. And so what happens is that, depending also on how the spiral is concentrated, if you have more points over here and so on, but it will tend to, because essentially, for example, the cosine function tends to spend more time here than here, then you're going to see more points here than here. And then when you see k-means over there, you're going to pick this guy and this guy, which corresponds to, this part and this part. And then in between, there's going to be a little bit of problems towards the middle, but at least, it's not going to pick, it's going to pick this guy, this portion with this portion in the same cluster, as opposed to thinking that this guy should be with this guy over here. So it's really about properties of the spectrum of the Laplacian, that they tend to do that. And the better separated the data is, even if it's entangled, the more kind of like conic structure you're going to have, that this tends to accumulate in these orthogonal entries. So k-means is going to have a much easier time with this.
Okay, so let's thank Nicolas.
So, first let me thank the organizer for inviting me. I was also in the first conference of the series. At that time I used the blackboard, and now I'm using slide with Guillaume, which is way younger than me, still using the blackboard. Yeah, it's kind of okay, so the talk of today is about optimal transport, multi-marginal optimal transport. and limit in density functional theory. I will explain both terms in a few seconds. It's a joint work with Giuseppe Buttazzo, Thierry Champion, they are here in the room, and Guy Bouchité in Toulon, and they will appear in one of the next slides too. So, we have seen several times in the last few days the multi-marginal optimal transport, but let me recall once again what we are talking about. We have n space, n sets, and we have a probability measure on each of them, and then we have a cost which is defined on the Cartesian product, and which may take the value plus infinity for me, okay? In my case, the cost I will consider is also bounded below, but there are around costs which are not bounded from below 2. Then I will consider the space of transport plan between this set of measures, which are probability measure on the product space, which have assigned marginal. And of course the marginal are the measure we considered before. And we try to minimize the linear cost of the transport plan. Here n will be greater than 2. Of course, even n equal to 2 is multi-marginals, but the nature of the problem is deeply different. So whenever we say multi-marginal, we usually mean n is at least 3. There are good examples of costs, and many of them have this structure, which is that they depend only on the mutual distance. This is not a distance, of course, but let's say the mutual distance between two points. The most natural class is this one, you see, and just to say about the difference, we heard already about that in some of the previous talk. These costs, which are considered easy for the case of two marginals, are very difficult for the case of n marginals, and only the case p equal to 2 it's completely understood. And even in that case, things work not because of a general path, but because of some special, I would say some lucky passage. The problem of optimal transport map may be formulated in several ways. In this case, what we mean by optimal transport map is the following. We look for n-1 maps, all defined on the first space x1, and they go on xi, and they push all the first measure to the ith measure. And we hope that the cost, here I'm missing, okay, here there should be 0,1, I don't know what happened. Okay, there should be 0,1. The value of this cost should be the minimal value. So I'm saying that the cost supported on the graph of the TE, it's minimal. I mean, it's optimal. And there are several papers. There are several papers on the existence of optimal transport map by Guillaume and Nazaré, Gangbo, SVH. They studied the case of the previous slide for p equal to 2. There is a paper on the Coulomb cost by myself, Simone Di Marino, and Maria Colombo for the one-dimensional case. Then Asif Gossub, and then there is a paper we heard about yesterday, I think, by Simone Di Marino, Augusto Gerolin, and Nenna, about the case of a repulsive harmonic cost. And we have seen several examples yesterday in the talk of Tapio. Here I will be interested in this cost here, the Coulomb repulsive cost. So, as you see, it's unbounded. It's bounded below, but it may take the value plus infinity. And before I go, well, let me see. Here, okay. Well, yes. Since the cost take the value plus infinity, there is the first question, which is when it is finite. For which row the cost is finite? This problem is the topic of a paper by Ugo Bindini. We should appear at some point on the Canadian Mathematical Journal, and another paper by Maria Colombo, Simone Di Barino, and Federico Stra, which should be forthcoming in the next few days, where we divide the ρ in two parts. We take the atomic parts of ρ, and we take the rest of ρ. The part which give you more problem is the atomic part, because in the Coulomb cost you have 1 over xi minus xj. If you have an atom, you risk to put the atom over himself, and the cost will take the value plus infinity. So what we know is that if the atoms are small, smaller than 1 over n, then the cost is finite. If the atoms are equal to 1 over n, then the cost could be infinite, and there are examples in both of these papers. And then in this second paper, there is a characterization which said that whenever alpha I is equal, if there is an atom which has weight 1 over n, then you should look at the rest of the measure and see what happens in that point. If the rest of the measure is integrable, then it's fine. This is the equivalent. This is equivalent to the finite moment condition for the p cost in the two marginal case. Okay, so what I will be interested in it's the regularity of the cost of the functional. So first, let me write what. Let me report here on the blackboard. So C of ρ, what I call C of ρ, I said it's the minimum among all the transport plan which have as marginal ρ of the integral. Here I get a sum on 1 smaller than or equal to e smaller than j smaller than or equal to n of 1 over xi minus xj dp. And I consider the functional which the nonlinear and non-local functional which associate C of ρ to ρ. And I will be interested on the regularity of this functional in some sense, because it will appear as a term in a more complex function, a more complicated functional. And I will be asking whether it's continuous or slower semi-continuous, whether I need to relax it or not, and so on. So when I want to consider the regularity, what I really need is to construct some transport plan. It's to test the functional, which is its value if ρn is converging to ρ, is C of ρn converging to C of ρ, and then I need to evaluate how much C of ρn, which is the value that C of ρn take, and then I need to construct some p, which is a way to construct some p. A good way to construct some p is the following. Assume that you have a measure ρ in the plane. Then you can take slice of the plane, different slices. Some can be very big and some other can be very small. And each of the slice has a weight 1 over n. And you may see that there are trouble. If you have atoms, when you take slides, you could have a problem. And then you build a map in some sense. What you do is you move the first slice on the second one, the second slice on the third slice on the fourth, and so on. You build a map T. And then you consider the identity times t squared times t to the power n minus 1 sharp of ρ. So each of these map is moving ρ on ρ. What will be t squared? T squared will move the first slice on the third, the second slice on the fourth, and so on. So you will never put the same slice over herself. And so you could be lucky, and this should be finite. Okay? This should be a good way. Then if you take smart slice, you may have also something which is almost optimal. Okay? This is a standard way. Another way could be taken, if ρ is very concentrate, you could have a ball here of weight 1 over n, another ball here, weight 1 over n, another ball here, weight 1 over n, and then you send the ball, the first ball on the second one, the second on the one. You see, it's the same idea, made with ball instead of slice, but the basic idea is divide your measure in n parts and then start moving the first on the second and so on. This is a way to build a non-optimal probability transport plan. In dimension 1 this is even optimal, but you can build a non-optimal transport plan which you may use to test the value of the functional. So the functional is defined on measures, on probability measures. So when you think about regularity, you have two possibilities. The first one is that rho n is converging to rho tightly, and in this case, what you have is that the rho is still a probability measure. In the limit, you don't lose mass. Or you may have that rho n is converging to rho weakly star, and in this case, you may lose some mass at infinity, and then you will end up on a sub-probability. So when you see this minus here, this means that you have something which has mass less than or equal to 1. It's still a positive measure, but has mass less than or equal to 1. And you wonder whether rho is continuous, or it is at least lower semi-continuous, okay? But you see, if you consider weak star convergence, then you need to extend the definition of rho to sub-probability. Okay? If you look here, you really don't care that rho is a probability measure here in this expression. Okay? So we are all tempted by putting this definition, by extending this definition to every rho in pi minus. Okay? If you have a sub-probability, you consider transport plan. They will have the same mass as rho. You consider the cost, and you minimize. And that's what we hoped to do for some time, but unfortunately this is not continuous and is not lower semi-continuous. Let me give you an example of why, what happens. With this, exactly with this kind of picture, I will have to erase because this is too small. Let me show you why this is not going so well. As a rho n, as rho, I would like to consider a measure on this ball, uniformly or distributed on this ball, which has mass 1 over n. So this is rho. And rho, so it's a sub-probability measure. Now I want to approximate it with a probability measure in the weak star sense. I want to approximate rho and look what happened to CO rho n. So which approximation I take, I add here n minus 1 ball very far away, okay? Each of them has mass 1 over n. They are all copy of this, and they are far away between them, between each other two, okay? And now I computed the transport cost of this one. You see that the transport cost is very small because whenever I move one ball on the other one, the distance is huge, okay? When I send the ball to infinity, the CO rho is going to 0, okay? So the natural definition for this rho would be CO rho equal to 0, and this is not 0, okay? So if I want to get something which is lower semi-continuous, when I approximate a sub-probability measure with a sequence of probability measures, on this measure here, I should have CO rho equal to 0. If I get this one, that will be not, this extension of C will not be lower semi-continuous, okay? The regularity of the functional, which to rho associates CO rho, has been a topic of paper, joint paper with Giuseppe and Thierry, which appeared last year, and as the same results had an improvement in the paper I quoted a few minutes ago by Maria, Simone, and Federico, in the following sense. If you think about the tight convergence, assume that the atoms of rho are small, in the sense this was the constant for me, Giuseppe, and Thierry, and this has been improved, is sharp. This has been improved by Maria, Simone, and Federico to 1 over n, and this is sharp. Then 0, Then 0 is continuous at rho. And you have also something more. See, it's Lipschitz in several subspaces of P. When you consider subspaces of measure which have densities, for example, LP density, if you take a probability measure which have LP density for P greater than 1, then C is also Lipschitz. Okay, it's very regular. For the weak star convergence, we need to consider the relaxed functional, which is abstractly defined in this way. Okay, so I take the inf of all the lim-inf of C of rho n for rho n approximating rho, so that here I should get 0. Okay, on this measure I will get 0. This is the abstract version of the relaxed functional, but I need an expression. I need an expression in some way for C of rho. And then this is the content. This is part of the content of the paper I was saying about joint work with Gigli, Giuseppe, Thierry, and myself. We should have out a preprint this week, but maybe I'm optimistic, and that will be next Monday. Yeah. Okay. First, there is an easy fact, which is this one. Okay. It's the one which I pictured here on the blackboard. Whenever you have a measure which has total variation, a positive measure which has total variation smaller than or equal to 1 over n, then the relaxed functional will be 0. Then we introduce a different idea. The different idea is the following. Well, sorry, there is a 1 here, this should be 0. That would be a very complicated way to write that alpha is equal to 1. Yeah, yeah. Then consider alpha smaller than 1, positive and smaller than 1, and the rho, which is in the suburb probability. What I do is I define a transport cost which depends on rho and on alpha. I consider all the sub-measures of rho which have mass alpha. So alpha should have total variation smaller than the total variation of rho, of course. And I consider the transport cost of mu in this sense. So I'm using this functional. This is not a good definition for the relaxed, but I will use it. How I use it? I transport all the sub-measure with this cost, and then I minimize among all the sub-measures. And then what we get is this, that the relaxed functional is smaller than the partial transport cost for this strange value. And in the case n equal to 2, the two coincide. So the relaxed functional of rho coincide with this partial transport cost, which should be interpreted as a transport cost with the fractional number of marginals, as I will show later on. For this value, in the case n equal to 2 for this value, in the case n bigger than 2 probably with this value, but I'll be cautious and I will put only less than or equal here for the moment. Okay, so we now have an expression which is which we may use because it's in terms of a transport cost which we know how to compute. I mean, we know how to calculate it. Okay, where is going to appear the what is going to appear the transport cost? The transport cost is going to appear in this variational limit, which I will consider. So you see, here I want to consider the limit as epsilon go to 0 of this strange functional. Here we have the gradient of the square root of rho squared. Then we have b, a parameter b times the transport cost, which is the one I was considering before, and then we have a linear term in rho. Rho will belong to this space. You have already seen this. You have already seen all. Well, you have already seen this one. You have already seen this one in the talk of Ugo Bindini yesterday. This is a space which was introduced by Lieb in 1983, and it's the right space to consider some quantum mechanical problem in the setting of density functional theory. V will have a particular expression for me. V will be V will be a special function V of x will be minus, no, I have a minus there, so V will be the sum for E which go from 1 to, from K which go from 1 to M, or 1 over x minus xk, and here we'll have a zk. So we will be a Coulomb interaction with a finite number of points which have a weight, positive weight. So what kind of function? Sorry, wrong. Okay. Okay. So this is a diffusive term, okay? Because you take the gradient, so you want rho to be a little bit spread around. Then you have the transport. Again, I should solve. Okay. Then you have the transport term, which also would like to send rho away, and then you have this one. What's the action of this one? This one is attractive because there is a minus, so you want this to be very big, and so you want x to be close to xk, okay? So these are like nuclei attracting x. This is pushing x to stay a little bit, not too close to xk, and this is diffusing a little bit, okay? I could consider this one. I could consider also square root of rho equal to u, and then you would get the more familiar expression, because you see you have the energy of u, and this would also give you a Schrödinger type equation, because you have the constraint u squared equal to 1. This would give you a Schrödinger type equation, but that wouldn't make too much. Well, it makes sense for fixed epsilon, but when you send epsilon to 0, the only things that this energy give you is that u squared is bounded in the space of measures. So it would converge to a measures, and doesn't make sense to consider u squared when epsilon go to 0 then, unless you want to make the passage. So this is the limit we want to consider. This is the first term will be called T, and it's the kinetic energy. There should be epsilon here. It's the kinetic energy. I will explain why it's the kinetic energy. The last one, it's the nuclear electrons interactions, and the CO rho represent the electron-electron interactions, okay? So if rho is the electron density around in the space, CO rho is trying to keep the electrons away from each other, okay? Because if they get too close, Xe minus Xj will explode. This term is trying to keep the electrons close to the nuclei with a weight zeta k, and then you add the kinetic energy, of course. Okay? The framework is the framework of Thomas Fermi theory, or density functional theory. It has origin in the 1927. There are two papers which came out at the same time by Fermi and Thomas, in which they started to think about this. They wanted to describe a quantum mechanical model in terms of density in our tree. If you think that the paper of Schrödinger introducing the wave quantum mechanics was just the year before, was 1926, they had already understood that computing the wave function was very difficult, and so they were trying to describe the models in terms of the electron density, which was measured on our tree and not on a big space, because wave functions are defined on R3n, where n is the number of electrons. Then this everything restarted in some sense. There is no true discontinuity, but here in the 60s and 70s there's been an explosion thanks to Hohenberg and Kohn-Sham, and then modern mathematical foundation have been posed by Mel Levy and Elliott Lieb in the beginning of 80. Why there is this gap? There is this gap because although describing everything in terms of rho was easier, one idea was missing. They were wondering how to describe the fermionic nature of the particle in terms of rho. In some sense, rho doesn't capture a certain behavior of the particles, which are captured instead by the wave functions. So in this time, there is a gap. And the gap involves the non-locality of the functional, as I will show later on. Okay, so the way of quantum mechanics, as I said 1 year before, was writing everything in terms of psi. So you have kinetic energy, electron-electron interaction, and nuclear electron interaction, exactly as in the functional I showed you, but everything is written in terms of a wave function. The wave function represents the probability that the electrons are in a certain position. Okay, if you rewrite the potential V as I did here on the blackboard, then everything comes like that. Okay, so at the beginning they didn't care too much about which were the relationship between the two. In the 20s they didn't start studying which was the relation between psi and rho, but then this was done in the late 70s. The natural idea was that rho was n times the first marginal of psi square. Because psi square is the probability that the electrons are in a certain position in the n product space. So if you integrate out n-1 variable, you get the probability that it's in a certain position. Then there is this n, which is a very good normalization for certain things and not for certain order. Then there is the reason why Lib introduced the space H. The wave function, the admissible wave function, are 1-to-1 with the rho in the space H, which I introduced before. And then there is the question of bridging between the two energies. So the first one is this one. The kinetic energy will correspond to our kinetic energy. The linear term will correspond to a linear term, and is fine. And there is this problem here in the middle, the electron-electron interaction. We don't know what to do exactly with the electron-electron interaction, okay? As I said, there is a problem with the fermionic effect in the sense that psi could be antisymmetric with respect to the xi, but once you integrate out n-1 of this, what does it mean being antisymmetric with respect to only one variable? You see, so here is the point where they missed the fermionic nature, and this was recovered by Hohenberg and Kohn by considering another kind of kinetic energy, which, as you see, it's non-local too, because the energy here, the energy of rho in a point, well, you see, it's not an energy in a point x. Here, the functional is local, depend on rho of x, while here it's a minimum among something and doesn't depend on rho on x. So this is one a supplementary non-locality to the functional. They tried, for the electron-electron interaction, they tried a lot of things, and what we will lose is this one. What we are using is this one, okay? So Thomas Fermi tried this, which is called the R3 functional. Then for several years, people still try correction to the R3 functional. What we are doing here is to use the transport term, the Coulomb transport, as an interaction, electron-electron interaction. The first idea was due to Michael Seidel, and then together with Giuseppe and Paola Gori-Giorgi, and also Codina Kotter, Garo Frisik, and Claudia Klupperberg, we all tried to lay foundation, mathematical foundation based on the optimal transport for this kind of model. So here there is, you see, there is the non-locality of this functional. We are considering the case with this kinetic energy, so the non-locality is due only to 0, okay? We denote by m epsilon the minimum, and the limit, we want to study the limit, and we want to study the limit of the minimal value and of the minimizers. Let me give you two motivations for this. The first motivation is this, that the transport cost, 0 rho, is a semi-classical limit of this functional. You see, I killed the last term. I eliminated, I don't have a nuclear electron-nuclear interaction, but it's also the limit of the fermionic energy, the Hohenberg confunctional I showed you before, and this has been proved by myself with Ugo for some n, by Claudia Kotter, Frieseke and Krupperberg in more general setting, and by Lewin also in more general setting. But this energy is not continuous. So when I add this term, I cannot deduce anymore the limit from this one. And indeed, when I add this one, the limit is not semi-classical, it is stay quantistic, in the sense that we will find that there is still kinetic energy in the limit. The second motivation is that since the minimum and epsilon go like this, go to minus infinity like 1 over epsilon, we should rescale again, and this is equivalent, I will show you why, and this is equivalent to this new functional. You see there is no epsilon anymore here, but there is an epsilon here under the nuclei. So in some sense we are taking the energy of a particle or an aggregate of particle, and we are sending the nuclei away from each other, and we wonder whether we will get something which is not interacting. We will get some atoms which do not interact with each other, okay? And this is known in quantum chemistry as the bond dissociation problem, because they expect that a molecule will break in several non-interacting parts. Okay, there are 3 easy ingredients, which is the behavior of the functional with respect to the change of scale and to translation. On the probability measure, I can change scale in this way, of course, and I can translate. And then there is the fact that the transport term is positive, so the energy I'm considering is controlled from below by the non-interacting energy, okay? So I have a control from below. So if I make a first analysis, since the 3 terms have a different behavior with respect to the rescaling, you see, when I put a rescaled measure inside the kinetic energy, I get alpha square. The other 2, they will get out alpha. This allows me to compute in some sense the behavior of the minimal value. I make a double minimization, I rescale. I put a measure inside, I can rescale it and minimize among this rescaled, and then I minimize again with respect to measure. And then easy algebraic passage bring you to the fact that the minimum of f epsilon behave like this, okay? You get the same if you have many nuclei, because when you have many nuclei, you don't have any more homogeneity of this term, but you can get a control from above and from below, and again you get that the behavior is like this, okay? So very reasonable to consider to multiply everything by epsilon, and again, using the rescaling, you obtain the bond dissociation problem which I presented before, okay? So the homogeneity of the 3 terms bring you to this functional. The limit I'm considering is the gamma limit. So these are the things I have to consider. As usual, if you are not familiar with gamma convergence, I don't know how many of you are. The gamma limit require you, the estimate of G minus require you to estimate every sequence, to estimate the energy of every sequence converging to rho, while the gamma lim sup require you to produce a specific sequence, a specific approximation of a measure rho. Whenever the 2 coincide, I say that the limit exists. And then I try to compute the limit. I will use as a model the non-interacting case. So here I cut away, in some sense, the non-local part of the energy. I have eliminated the transport term, which I have not anymore on the blackboard. I'm still pointing to the blackboard, but it's not there. And you see the functional now, it's a little bit easier, and we know it very well in some sense. We know that the minimum has this value, and we know also the minimizer. This is a very well-known problem is the first Schrödinger eigenvalue, which is negative. It's minus here. It's minus 1/4. Friends from physics tell me should be minus 1/2 because the energy of the atom of hydrogen is minus 1/2, and this depends on the fact that I didn't put the 1/2 here. Okay. The kinetic energy usually has a 1/2 in front. Then well, this is then if I try to do this with several nuclei, so it's not anymore the hydrogen. The hydrogen is the particle with only one nucleus. What we can prove, and it's reasonably easy, it's this, that the gamma limit exists and is given by this functional. Okay, so the gamma limit consider only the value, the atoms of rho, which are concentrated on the nucleus k, and if you look at this in the right way, you see that this is in some sense the energy of the hydrogen multiplied by zeta k squared. Okay, so the energy of the hydrogen was minus 1/4. Here I get there should not be. I think this n should not be here. I think this n should not be here. Okay, so you see, in some sense, what we get is the energy of the hydrogen in each of the nuclei, and there is no interaction. But there was no interaction before too. And here you know easily. You easily know which are the minimizer. Of course, if you want to minimize this quantity, what you will do, you will put the maximum possible rho on the biggest zeta k, okay? Because here you get there is minus here in front. So if you concentrate on the xk, which have the bigger zeta k, you get the minimum. And this is reasonable because electrons don't have any reason to stay away from each other, because I took away the interaction, the electron-electron interaction, so they go to the strongest nucleus and they stay there. Okay? So this was the toy model, but you see that if you study the model with one nucleus, then you can try to deduce the model for many nuclei, but you have local energy here, so localization is easy. Okay, now I want to do the same for the interacting case, but then I need to introduce what I call the energy of a strange atoms. Now, a strange atom, I will tell you why it's strange. It's strange because what I'm doing here is considering the inf among all the rho which have mass alpha of the kinetic energy plus transport plus the interaction with the potential with the charge, positive charge zeta, and this strange transport term. It's a fractional transport term I introduced before. It's related to the relaxation of transport cost. And this should represent the energy of a single atom which has a nucleus in 0 and charge zeta, and how many electrons? That's an n times alpha electrons. But you see that depending on alpha, n times alpha could be non-integer. So there is a fractional number of electrons. But we are not the first one who consider this. In the 1982, there is this paper of Levy and co-worker, which start to consider this idea of fractional number of particle. And then there is a more recent one in which they study the discontinuity of the derivative of the functional. What does it mean having half electron? Half electron means that you have two nuclei, and there is one electron which is going around between the two. So it's spending half time with one and half time with the other. And so this is, in the model, this is like having half electron, okay? So we decompose the measure in this way. We consider the concentration of rho in the nuclei and the rest. Why we do this? Because we expect that when epsilon gets smaller and the measure can concentrate, it will concentrate around this point because there is a minus in front of the term. So the electrons want to go to the nuclei. And we need another tool, which is the localization. Localization, what does it mean localization? Localization means this. Take a probability measure ρ and take a cutoff function theta, which is equal to 1 around the nuclei, which is the place where ρ want to go, and multiply ρ by theta. This will not be a probability measure anymore because you lose something, right? When you multiply a probability measure by a cutoff, you lose all the mass, which is where theta is equal to 0. Well, okay, then you complete it. You add the nu. Nu is just something far away. You add the two balls somewhere far away, and you want to know how much you perturb the energy. You perturb the energy. Well, okay. We know that it's perturbed by epsilon times this strange constant. This is constant in some sense. Well, there is another epsilon here, but actually you can control everything by a constant, which takes some time to work out explicit. And the fact that I'm assuming that n is equal to 2 is related to the specific representation of C bar I'm using. We have a more general representation which is less suggestive from physical point of view for a general n. And when you want to localize, the transport term is the problem in this case, okay? Because the transport term is non-local. So when you cut off the function around a point, you get in trouble with the transport term because something was moved somewhere and now there is not anymore, okay? If I have something here which is moved down there and the cutoff function is 0 there, I cannot move that anymore. Okay, so the transport term is the problem. It's the non-locality of the transport term is the problem. Okay, what we can get then? The first thing we get is this, that for n equal to 2, again, this is related to the specific representation. Whenever you get a ρ sub-probability measure, the g, the gamma limit functional exists, and it's equal to the gamma limit functional on this concentrate part. Ρ is still this one, okay? It's the sharp part is the part of ρ which is concentrated on the nuclei. And then that we have a formula for the gamma limit, which is this one. So what I'm getting here, look, here I have the sum of GB of zeta I alpha I. But what is this? This is the energy of a single atom with the fractional number of particles alpha I. So in the interacting case, I obtain the same result as in the non-interacting, but with fractional number of particles and fractional interaction in some sense, or if you want, partial optimal transport, okay? So in some sense, we can represent the gamma limit. What should be true in general? Well, okay, more, and I can also make an analysis of the minimizer of this functional. Once I get the gamma limit, I want to know what's going to happen, and I get this. If I make a easy analysis for n and m equal to 2, so 2 nuclei, take for example a molecule of H2, two hydrogen atoms. What I get is this. I want to minimize the sum of these two with respect to this. So I take ρ, which is the combination of the two nuclei, and I want to minimize this with respect to the alpha, to the weight I'm putting on the two particles. Since I know some property of GB, which is convex and so on, whenever zeta 1 is equal to zeta 2, the minimum is attained for alpha equal to 1/2, and that's the breaking of a hydrogen molecule. Whenever zeta 1 is greater than zeta 2, the minimum is attained for alpha different or 1/2, so it is not true anymore that particles are going to the heaviest nucleus. The interaction now has an important. And I also said, without saying it, I also said that in some sense the minimum is attained on probability measures, because you see, I started directly with this. I'm tricking in some sense, but we know that, we can prove that. So, when you break a molecule, there is no loss of electron at infinity, okay? So this is a side result of this theorem. So, the result is divided in two parts, in some sense. What we have in the case n equal to 2, and we are working out in the other case, is that G of ρ depends only on the restriction of ρ to the nuclei. So when you send to zero the kinetic energy, the molecule will break around in atoms, and each atom will get its share of electron, and the electron will still interact between each other. The second thing is that there exists a function Gb, which is the energy of an atom with a fractional number of electrons, such that G has this representation. Okay, so we have a general formula for Gb for any n. The point is that it's not so clear. We can't make it as nice as in the case n equal to 2, where there is this partial transport. In some sense, there is this partial, and that's what we like to use to optimize. So let me make a short summary and tell you some perspective. We considered the problem and we tried to describe correctly the bond dissociation, and this helped to understand that the transport term, the optimal transport term we use in the modeling, it's a good term. The term proposed by Seidel, Paola Gori-Giorgi and co-worker is a good term. And we got an explicit formula for the case n equal to 2 and the general structure for the theorem. I know we now know which are the passages which we need, which is the formula that we need. What we have in progress is this: we are trying to produce a nice formula for C bar. You have seen the formula in some sense, but I put it around with an inequality. I didn't discuss the existence of minimizer for f epsilon. That's what is called the ionization conjecture. And it tells you which should be the equilibrium between the number of nuclei and the number of electrons to have existence of minimizer, because if you put too few nuclei, some of the electron could escape at infinity, pushed away from the other. And whenever you change one of the terms in your quantum energy, then you have to reprove, you have to study the quantum. And this is related to the relaxation. And we are working out a representation, a general representation for G for any n and m. What we look forward to is to have a numerical and theoretical study of the minimizer of G. That's why, because we know where, more or less where they are, know how much weight I should put on one of the nuclei, how much I should, but not exactly. And we would like to understand better how do the molecule break. The ideal situation is when they break according to the positive charge. In some sense, you have only neutral atoms, but this is not possible for two reasons. One is that you don't have enough charge sometimes. The other one is related to the transport term. The transport term doesn't break exactly them. And then we also look forward to the idea of finding some localization property for the Hohenberg and Kohn kinetic energy, which, as I said, is non-local, to deal with fermions. And this is related to the talk of Ugo Bindini yesterday. Understanding how psi go to rho should help you to find a localization theorem for the non-local kinetic energy of Hohenberg and Kohn. And I have hope and dreams about other physical functionals which don't have representations. In some sense, there are several functional rho which cannot be represented by integrals, but are related to something in psi. So if we can understand a little bit, we could have a localization also for this functional which don't have an easy representation, like the gradient of the square root square or things like that, okay? And on this I will thank you for your attention.
Okay, so for general n, do you think that what would be the easiest one, 3, 4, or any n?
I think, well, 3 should be easy in some sense, because when you relax the transport term, you get to transport with less particles. So from 3, you cannot go far away. You can get to 2 at most. While for n, we expect... Yeah, that's no. We expect that yeah, the representation will involve something, but we hope to get a formula.
So the next and final talk will be given by Leonard from Paris-Nanterre.
Yes.
And this will be on optimal transportation and LDP.
Large deviation principle.
Which is quite appropriate to after the talk of LDP.
LDP. Yes, LDP. Thank you, Jan. Yes, and well, of course, I thank the organizers for giving me the opportunity to be once more in Pisa. It's always a great pleasure. So well, I'm going to talk about connections with large deviation theory, which is part of probability theory, and some aspects of optimal transport. So I assume that you don't know anything about large deviations, okay? And I will be very sketchy and try to convey a couple of ideas. So you will recognize at some point some talks about the Schrödinger problem, and also this will be connected to gradient flows with the talk of Alex Mielke. And at the very end, if I have time, I will try to show a program for a work in progress about mean-field games and connection with large deviations of large systems of particles. So I decided to begin the talk with the simplest problem I could imagine dealing with optimal transport and large deviation. So namely, this is a concentration of measure result. The interest is not this result because it's well known for a long time, but the method of proof. Okay, I will try to be as pedagogical as possible. So consider the following Fokker-Planck equation: dTm plus divergence of mv, where v is a velocity field, equals Laplacian of m divided by 2, because I do probability theory, so I divide by 2. And the initial condition is m0 is a Dirac mass at some point x. All right. Then the result is as follows. At some time capital T, you evaluate the measure mt, which is solution of this Fokker-Planck equation, of the complementary set of a blow-up, a R enlargement of some set A. And this is less or equal than the exponential of minus positive part of R minus R star squared, where R star is something with log of 2, something which is universal. You divide it by 2 times tau. Tau is a positive constant, which is homogeneous to a time. And this will be true for all set A, such that mt of A is greater than 1/2. True for all enlargement size R, all capital T, all initial measure, initial state X. Of course, we need some assumption. And this is a curvature assumption, and the hypothesis is on the velocity field V. So Vt of y minus Vt of x, scalar product y minus x, is less or equal than minus k over 2 square norm of y minus x. This is true for all x, y, and t. So this is a typical large deviation result, and now the constant tau should depend on the curvature k here and also on the time t. And you can evaluate it, and it is with this method, which is a rough method, still you get the good constant. So tau of tk is equal to 1 minus exponential minus kt over k. So in particular, you can see that to infinity k is 1 over k, which is the usual Gaussian concentration measure. And at time 0, tau of 0, curvature 0, tau of t and 0 is simply t. So you've got the blow-up of the heat kernel, a rough blow-up of the heat kernel. All right. So how does this proof work? Yes. The idea of proof is as follows. Oh, before I proceed, I should say that this is part of a joint work with Yvan Gentil and our PhD student Luca Tamanini and Luigi Ripani. It's one of the results in their thesis. And the idea of proof is as follows. You want to have a smart representation of MT of A. Now, take any set A. In a moment, you will choose A as being the complementary set of the blow-up AR. And the way to compute it is you compute the probability that for all, so, no. Okay. I have to introduce some stochastic differential equation. So dzt is equal to dt of zt dt plus dbt, and at time 0, z0 is equal to x. So the solution to this stochastic differential equation, where b is the Brownian motion, the law of that t is precisely mt. Yeah. Okay? And now, so I write it, mt is the probability that t belongs to some dot. Now you consider independent copies of these particles. So you have an infinitely many particles which are tagged by I, and all the BIs are independent Brownian motions. All right? And what we compute now is the probability that for the n first particles at their position at time t in the set A. So if A has not a full support, this is a rare event when capital N is large, because you can compute this very easily. Because of the independence, this is nt of A to the power n. And if nt of A is strictly less than 1, this goes exponentially fast to 0. So this is a large deviation from a law of large number. Okay. Now we introduce the empirical measure that at n of the whole trajectories here, so which is 1 over n, sum of the Dirac masses at zi. So this is a random element on the set of all probability measures on the path space. These are path measures, random path measures. Okay. And now this evaluation here, this probability, you can write it in the following way. This is the probability that hat n at time t of A is equal to 1. I put t here for, if you put t here, you put t here. So this is the empirical measure of the position at time t. Okay? All right, this is just playing with writing, but at this step, we are going to use a large deviation result, my preferred large deviation result, which is Sanoff theorem, and I write it without detail. So this is true for any empirical measure of IID sequence. In particular, in this situation, so the probability that at n belongs to some set dot is essentially, when n tends to infinity, exponential minus n times the infimum of the relative entropy of P with respect to R, where P belongs to dot. So I have to give some explanation. R is simply the law of the common law of the particle. So the law of Zi is equal to R. It belongs to a probability measure on the path space omega. Okay? And the relative entropy of P with respect to R is the integral of the whole path space of the logarithm of the Radon-Nicodim derivative of P with respect to R integrated with respect to P. And this is a non-negative value, possibly infinite. Okay, usual relative entropy on a huge space on omega. Okay, so if I have time, I will give you a hint for at the end of my talk for the appearance of this relative entropy. Okay, this is playing with Stirling formula. This is a clever combinatoric formula. Indeed, you can see it this way. So this is Sano's theorem. Yeah. Now, if we go back to what we are calculating right now, so and using the Sano's theorem, what we can say is that logarithm of mt of A minus logarithm, it will be easier, is equal to 1 over n minus log of mt A to the power n, of course. And this is equal to 1 over n log probability that at n of A is equal to 1. And now we take the limit in order to use the Sano's theorem, limit as n tends to infinity, and this is infimum of the relative entropy of P with respect to R computed over all P's such that Pt of A is equal to 1. And this is the clever formula. So now we would like to have an expression for this infimum. So I draw a picture where here we are in the space of path measures. Okay, R is here. The relative entropy is a strictly convex function, so I draw level lines. So this is H with respect to R equal constant. Here is a potato here, which represents the set of all P's such that Pt of A is equal to 1. And here there is a probability which I call PA, and which is the minimizer of our problem. So this is equal to HPA with respect to R. You see, you've got, it's unique because of the strict convexity of the relative entropy. So the clever formula, and this was used maybe in a different way by Christoph Boyle in different situations, is minus log mt of A equals H relative entropy of PA with respect to R. So, okay. So now you could compute this directly without thinking of the particle systems, but this is a useful guide. So what can be said about this relative entropy? So this is a general result, and the relative entropy of P with respect to R, where R is given by this stochastic differential equation, is the relative entropy of the initial marginals, P0 and R0, plus some dynamical term, which is the expectation, so integral over omega of integral over all times, 0 infinity, of some what could be called a vector field, alpha t squared, I take the norm, dt. And integrated with respect to dp. So what is the connection between p and alpha? So think of alpha as a vector field, but a random vector field. To be really precise, this vector field should be called a drift field because it depends not only on the actual position, but on the whole path of the trajectory. Okay? And the result is that if this relative entropy is finite, then there exists some alpha such that you have this representation formula, and also that dxt, I'm writing a stochastic differential equation such that P is the law of this, the solution of this stochastic differential equation. So you have Vt of xt plus alpha t, this is the extra drift term, Vt plus dBt. Okay? And the law is P. Okay. So if we take this for granted, we are close to the solution. So the proof works as follows. Now we start from x, we are in Rn now, and if you play your reference measure, then you will get a sample path going everywhere this way, and it should not hit the set A in general, but under PA, the drift field alpha, as the action it blows on the particle so that at time t, xt is in A. So you have to pay something such that at time t your particle is in A and the cost is here. This is really stochastic control, for those who have any connection with stochastic control. Okay, now let's introduce another set, B. In a moment, you should think of B as being the complementary set of the blow-up of the R enlargement of A. And now, so this is under PA, and under a loop PB, at time t you are in the set B. So the xt is equal to this, and we have the yt is equal to dt of yt plus some drift field beta t plus dBt. Now the idea is very common in probability theory. Choose exactly the same Brownian motion for these two particles. This is a strong coupling, which is called the synchronous coupling, and same Brownian motion. And this is the place where coupling comes into the picture. And what you obtain is that the difference of y and x now satisfies an ordinary differential equation, which you can write. This is dt of yt minus vt of xt dt plus beta t minus alpha t dt, and dBt cancels. So this is an ordinary differential equation which is parameterized by a random parameter. Now, there is our assumption on the vector field V allows you to to do some Grunwald lemma, and then you will get an estimate. The square of the difference of yt minus xt should be less than some constant depending on k, the curvature, capital T, the time, and the integral over 0t of beta t minus alpha t squared. I divide it by 2, and this is something. So you play with Grunwald lemma. You have usual trajectories to do that. They have a bounded variation, and this is all right. Now, if you choose B in this way, and for those you who already know, we mimic the proof of Katalin Martin to get a transport inequality. What you know is that the distance, so think of B as being all the complement now of something which is a blow-up. Then the distance here is at least R because of the definition of the blow-up. So the distance between A and the complementary set of the blow-up AR is equal to R. Okay? And therefore, this is the norm of yt minus xt is certainly greater than R. And we are done. We have a good estimate there. And to complete the proof, what we want to do is now minus log of mt of B with this choice of B. This is really what we want to estimate, is equal to the relative entropy of PB with respect to R, which is equal to the expectation and the, well, I say an expectation because we have a coupling on the time interval 0t of beta t square over 2 dt. And to conclude, simply write that beta square over 2 is greater than beta minus alpha square over 2 minus alpha square over 2, which is not true in general. So you introduce this one. You introduce a parameter, 1 plus theta here and theta here, and optimizing on theta, this is always true for theta greater than 0, then you get the result with the good constant. Okay, so what is really interesting here, in some sense, what we have built here is a stochastic optimal plan, an optimal stochastic plan, where we have coupled xt with yt. So you can see it as a stochastic version of a Monge-Kontorovich plan. And it's not far from being optimal in some sense. Okay? The question of knowing if we reduce the noise with an epsilon dBt, does it converge to the solution of some optimal transport problem with a quadratic cost? I didn't do the computation, but I guess yes. Okay. All right, so this is the first part of my talk. And now I would like to evocate some connection with gradient flows, very much in the spirit of Marc Peltier's discoveries of the connection between large deviation and gradient flows. So the inspiring paper was the seminal paper by Adams, Deer, Peltier, and Zimmer more than 10 years ago about the connection between large deviation and some gradient flows. So what about gradient flows? Again, I will talk about something which are already known, and you will see in passing that it will be very close to the talk by Simone Di Marino. and mainly, and with close connection to Alex Milke's talk too. Okay? So, what is the gradient flow we have in mind? Essentially the same as before. dTm minus divergence of m gradient over capital U over 2 is equal to half Laplacian of m with an initial data, m0. Okay, the result is well known. The solution of this Fokker-Planck equation is the gradient flow. So is the W2 gradient flow of the entropy with respect to m infinity in the space of probability measures on Rn, where m infinity is the limit of mt as t tends to infinity, and this is the equilibrium measure exponential minus u times Lebesgue. Well, suppose that u is normalized an additive constant such that this is really a probability measure. Okay? So, well, I'm cheating. This is over 2 because I divide the Laplacian by 2. Okay? So this is really Felix Otto's result, and it's well known. So the connection with large deviation, this is not the way Marc Pelletier presented things, but I present it with Sanoff theorem now, and you will see it's very easy with Sanoff theorem. So now we have a stochastic differential equation again. Zt is equal to minus gradient u over 2 of zt dt plus dbt. And if you start with an initial law z0 according to m0, then the law of the solution of this stochastic differential equation is precisely this Fokker-Planck equation. Okay? But as a reference measure, I will take another guy, and this is the same dynamics, but at time 0, we ask for z0 to have the equilibrium law. And I call the solution R. R for reference, but also for reversible. Because not only at each time t, RT is equal to m infinity, so you start from the equilibrium, so you stay at equilibrium. You don't see anything. There is no flow in some sense, constant flow. But also, in restriction to any time interval 0t, R0t is such that if you take its push forward by the time reversal, then you will get exactly the same R0t. So star is for time reversal. This is the law of the trajectory evaluated, and well, you reverse it. Okay? Time reversal. This is a detailed balance condition for probabilist. Okay? All right. Now, again, we are going to rely on Sanoff theorem. So consider many particles, you tag them by I, Zi, Bi, they are all independent, but now you don't start from Z0 equals m infinity. Oh yes, maybe I could, well, yes, I do it this way. And you have copies of this reference measure. What we would like to compute is a logarithmic rate of the probability that Z bar n is close to some mu. I will explain the notation, knowing that Z bar n0 is close to m0. So the notation Z bar is the following. Z bar is simply the collection of z add nt for all t. So this is the time marginal flow of the empirical measure. So this belongs to the continuous path from the time half line to the probability measures in Rn. So you see, there is less information in z bar than in z hat, because in z hat you can compute correlations, while in z bar you only have the empirical measures at time t. So this is at the PDE level, and you have more information at the stochastic differential equation level because of the possibility of computing random stopping times, correlations, and so on. So now, what we know by Sanoff theorem is that this is essentially exponential minus s, some function j m0 of mu, and j m0 of mu is equal to the infimum over all the entropies p with respect to r for all p such that pt is equal to mu t for all t, minus, well, the initial contribution, because since I conditioned on this, you have the log of something which is below the fraction line, and you get a minus here. Okay? All right. Now, we would like to compute this. So, this is a rather difficult part to compute J of mu, but this has been done by Dawson and Gärtner in 1807. So this is a long time known result for probabilists. Okay, but let's go back to the gradient flow. And what we do is we look at time discretization in search for a de Giorgi scheme. So take tau, a positive time state, which is not the constant before, okay, of the concentration of measure. And you consider Tk is equal to k times tau for all k. And you time discretize your process and define the time discretized process mu t tau as being mu of tau times the integer part of t over tau. Okay? So this is the piecewise constant approximation of mu. Now we have again large deviation principle for this piecewise constant approximation. So I write tau here, it doesn't change anything here. What you have is j tau, okay? And what is j tau? Simply, instead of conditioning everywhere, of asking that pt is equal to mu t everywhere, then you ask that this is only true for all k on your time discretization set, okay? So this is infimum, okay, is less than the one without tau, because infimum over a bigger set is smaller. By the way, this formula is called a contraction principle in the large deviation theory. So traveling from H to J is a contraction principle. Now, what we have in mind is to have a refined time discretization, and we have an inverse contraction principle, but this is not, we don't have the right to call it this way because it makes reference to another result in large deviation. So we call it, well, a projective limit of large deviation principle. Don't be afraid of this. This simply when tau tends down to 0, then the j tau will converge increasingly to j tau, okay? So because you add more and more information and you gain information. So it's incredibly simple. So what you get is this result is that J M0 of mu is equal to the sup over the refined time discretization, J tau M0 evaluated at u tau. And this is a gamma limit because this is an increasing limit. So this is the gamma limit as tau decreases to 0 of J tau M0 evaluated at mu. So what you know now is that the argmin are converging. And what is the argmin of J, mu0? This is simply M. This is the place where you have 0. You start from M0, and then this is the gradient flow that you have. This is MT. And the argmin of the same thing with tau, and we have this convergence, is simply m tau. Okay, this is the time discretization of this. So this result is stupid. Well, it's so easy. You say that a piecewise constant approximation converges to what you know. So, but this is not the relevant thing. The relevant thing is that this piecewise approximation can be seen as the minimizer of J tau. And now you can extract information from this J tau. And I don't get into the details, but this formula appeared in two previous talks during this week, in a talk by Luca Tamanini and also in the talk by Simone Di Marino. And it was based on previous results by Luigi Aripani, Yvan Gentil and myself, and also Chen, Georgiou, and Pavon at the same time. And what you get is that J tau M0 of mu is a sum of, for small times, of something like h over 2 mu tk plus 1 with respect to m infinity minus h over 2 mtk with respect to m infinity plus 1 over 2 and some large deviation cost indexed by tau of mu tk plus 1. Without getting into the details, you have this, and it can be proven that this large deviation tau rate here, which is a cost, I call it C because it's a large deviation cost, converges as tau decreases to infinity to W2 square over 2 of mu tk plus 1. By the way, this is not so easy to prove. There is this Fisher information that comes into the picture, and you have this Benhamou-Brognier Schrödinger formula that comes in. And to prove that you have really this convergence was not so easy, and it has been done by Jan Maas and Matthias Herbar and Michiel Renger. So you have to work a little bit to make these things very rigorous. So the idea, the rough idea, is that saying that the Fokker-Planck equation is the Wasserstein gradient flow of the entropy is, in some sense, it's more natural to say that it is the gradient flow with respect to this large deviation cost. Okay? And, well, these are two different pictures, but this is with the same idea. Okay, so large deviation here does really the work for having a gradient flow. So it provides us with some guesses. As soon as I can compute large deviation for particle systems, playing this partition should give me some results about gradient flows in some sense. In particular, it works all right if you are on graphs and replacing the Brownian motion, the Laplacian, by a random walk on the graph. At least theoretically, it's all right. This is exactly the same program. But when you want to do exact computation on a specific graph, then usually you become crazy, except for the complete graph. Okay, so there is a theoretical gain, but we are in front of a very difficult problem. So nowadays, this is mass and Milke theory, which is efficient because we can do explicit computation. But maybe in some future, we will be able to provide another way of looking at gradient flows on graphs. Okay? So maybe, do I have 10 minutes left? Yes. So, and now, what I'd like to introduce is this one. It's getting better. Maybe I'm stronger. I don't know. Probably there is some oil in the picture. So I'm stronger than Guillaume. All right. Okay. The last 10 minutes of the talk will be about work in progress, dreams and hope, and so on. So, but this is a work in progress, so towards, I will say, midfield games. Again, you will see from very far close connection to Pierre Cardaillaguet talk, and also to Simone Di Marino's talk about this, which is very close to this, but with the large deviation picture in mind. So, okay, we need now large deviation principle for empirical measures with interacting particles, because there are nonlinearity in Milton games. So this is the way we are going to introduce this nonlinearity. So the IT is equal to the drift field is VT, that IT, and also it depends on the empirical measure time t of the whole system. dt plus dBit, where the bi's are Brownian motion, which are independent. So this is the only difference. Suppose that you get a collection of all these particles. I consider capital N particles. I don't talk about the initial condition, but it is somewhere. And the law of this system of n particles, you call it Rn. It is a probability measure on the product space omega n, where omega is the path space. Okay? All right. It's possible to compute the large deviation principle for that hat n and that bar n. So the large deviation principle for the simplest one is for that hat n, is that under this dynamic, the large deviation LDP, large deviation principle, gives you a rate function I of P, which is equal to the relative entropy of P with respect to R, and in exponent I put P this way with brackets. And who is this guy? Simply, this is the law of the xt is equal to v of t xt pt, which is the law of x dt plus dbt. So what is strange here is that pt is the law of xt. So this is a nonlinear stuff. By the way, as a corollary of this large deviation principle, so this has been performed by Dawson and Gertner again, is if you look at the minimizer of this rate function, then this is the place where you converge. This is the law of large number of your problem. So as a corollary, you know that at n converges to the solution of p is equal to Rp, because the only minimizer of the relative entropy is the reference measure. Okay, so this is a nonlinear equation, and we call it Makin-Vlasov nonlinear stochastic differential equation. Okay. All right, and this is the way to introduce interaction. There is another way, and also once you have Rn, you can consider Run for the n particle system, where the Radon-Nikodym derivative of Run with respect to Rn is a Feynman-Kac integral formula. So minus sum of I equals 1 to n, yes, I would say, yes, I. Integral, well, we will restrict to the time interval 0, 1 here. Okay, and u of t, that it, that bar n t dt. So this is the exponential times Rn. Okay, suppose that u is normalized such that this is a probability measure. Okay, then we can call Rn R0n because it corresponds to u equals 0. So we'll put 0 here and 0 here for the rate function. And it's very easy under some regularity and boundedness condition, growth condition on u, to show that this satisfies the large deviation principle under this new law. Then z at n satisfies the LDP with the rate function Iu of p, which is defined by u, well, expectation with respect to p of the integral of 0, 1 u t xt pt dt plus I0 of p. So this is simply, if you think of this as being formally I0 of p, so R0n, you say formally that it satisfies the large deviation principle with I0, then what you get is a Laplace integral formula. So you will get this at the limit. Finally, I will quote famous results about large deviation and a simple consequence in terms of duality formula for mean field games. So suppose that z at n satisfies the large deviation principle with the rate function I of p. Okay, then the Laplace-Varadhan principle (1964), a paper by Varadhan, states that 1 over n logarithm expectation of exponential of n times f of z at n for a function f. Okay, if you consider the limit as n tends to infinity, it exists, and it is equal to sup over all p of f of p minus I of p. Again, you think of z at n is the law is essentially exponential minus I of p, and it works. Okay, it works. So under some graph condition, more very exciting result. The next one, which is the inverse Laplace principle, LV principle, also called Brick's lemma, and which is very easy to prove once you have the large deviation principle. If you call this limit lambda of f as a definition, then you have an inverse formula which tells you that I of p is equal to the sup over f, I don't specify right now, f of p minus lambda of f for all continuous and bounded functions. So we are used to convex duality, and with convex duality you restrict to affine function here. Okay? Now, if you take the class of all continuous bounded function, then you can reverse even if I is not a convex function. And of course, I should not be a convex function with such stuff, okay? So, and even more interesting, to my opinion, you can replace continuous bounded function by concave, upper bounded concave function. And why is it interesting? Because now, well, I'm running out of time, so I won't write the formula, but if you play now with the large deviation principle connected to probability that z bar n at time 1 is close to mu1, knowing that z bar n at time 0 is close to mu0, so you have a large deviation principle with a rate function which is a cost, a large deviation cost, where mu0 appears as a parameter because it's fixed, and it is a function of mu1. And if you play this formula, then what you obtain is C0, C mu0 of mu1 is equal to sup over psi of mu1 minus q psi of mu0. So I write a duality formula with some Hamilton-Jacobi equation on the space of probability measure, where psi is a concave function on the set of probability measures on Rn, on the Wasserstein space, okay? And q psi is given by this formula. So q psi, I write it here, q psi of mu0 is the limit as n tends to infinity of 1 over n logarithm expectation of exponential of n times psi of z bar n1 at time 1, knowing that z bar n0 is close to mu0. So, well, and if psi is an affine function, then we know that what we write is a Hamilton-Jacobi-Bellman equation in this situation. So, at the level of the state, the configuration space. But now we are at the level of the probability, okay? So this is work in progress. I don't want to say too much, but we have some hope with Giovanni Conforti, Julio Backhoff, and Yves Gentil to exploit this duality formula, which again is a classical result in large deviation theory. So thank you for your attention.
In Minfi games, some people care about the joint noise.
Oh yeah, the common noise. So it's
Can you
no. Well, with the common noise, things are becoming ugly. Well, I don't know if we can manage, but we didn't. Well, I've been in this Minfi game business for only 3 weeks now, so I cannot tell many things about this. Okay.
So maybe it's time to thank the people in You understand what this means? The three gods, the triad, Capitoline. Yeah, with Luigi, Giuseppe. And, I think also Dario played a very important role, and the staff of the Georgi Center. It's on. And so yeah, we saw Antonella few and I think we should really also thank Tatiana, because she was so patient with us running the. And I hope I didn't miss anyone. Okay.
We should also thank the unofficial organizers, so Dario.
Yeah, I said it also.
Oh yes, okay.
Yeah,
oh, sorry.
Yeah, but Dario. But Dario is the name of an emperor, so he deserves. Okay, thank you.